All right. I do believe we are live, boys and girls. Welcome, welcome, all of you here to do a bit of further maths with us. How are we this morning? Are we ready? It is bright, it is sunny. We've just had a great bank holiday weekend, although some of you might have been on the amazing Neil Does Maths' 8-hour streams all weekend. How are we doing? Good morning, it's Shruti. Good morning, good morning. Cube cores in the chat. Schlockapur doing D1. Well, that'll be fun. That will be with the Mighty Joe if you are signed up to our full ERC package. Yeah, 24 hours of maths, right? Across Saturday, Sunday, and Monday. That is pretty intense. That is lots and lots of maths. Hey, Richard. Hey, yo. Are you on the main course? Yeah, I think a lot of people have been watching the main course recorded. There we go. You didn't do the Sunday EMS. That's all the good stuff. That's where the good stuff is. Was that the applied? I can't remember how we structured it. What modules do we all do, Michael? Well, that's very interesting. I'd love to know what modules people do for further maths, the massive hodgepodge that is further maths. Right, before we get going, don't forget, if you do not have it, there should be a link in the description that you can go get yourself logged into the MyEdSpace platform, and where you can go and get not only your free workbook to follow along today, but also a core pure paper for you to practice everything that we're going to look at today and tomorrow. Of course, so that's all there for you. Just click on the link below. There should be a little banner sort of there. I'm sure there's an easier way. Look, that way. That is an easier hand to use, isn't it? So what are people doing? Oh, apply was Monday. So further mech, further pure, D1M1, FMFS, FMD1. Interesting. So when are the master classes, Kian, for further maths? Do you mean the exam master classes? The exam master classes, oh, that is a big question as I try and figure this one out for us. So basically, they are coming up over the next few weeks. Tell you what, remind me this question later on after we've had a break so that I'm not running around trying to get these dates for you. Just remind me after we've done just before a break, and I will get that information up for you. Why aren't there MyEdSpace? We are working on my revision notes, my resources for further maths. Just takes a while, right? We needed to get the normal maths out, and then we're now working on the further maths ones, but we are working on them. It will be amazing. Penguin doing FS1 and FS2. Oh, my man. That is amazing. I wish more people did FS1, FS2. Oh, that would be amazeballs. Love me a bit of FS2. Love me a bit of FS2. I always find that stats finishes just before it gets interesting. So what, you get to do a bit of students. What else do you get to do? Some non-parametric tests. What else is in FS2? I'm trying to remember. What's my favorite module, Malik? Probably the further stats. Probably the further stats. I think it gets really interesting. Really interesting. Step. Ooh, you're doing step. That is tough. I've put a few step questions up across Nick Does Maths and MyEdSpace Maths. Go have a little look, see that with them. Malik, FS1 or FS2? The whole thing, really. The whole thing. FS1 is cool. FS1 is cool. Probably, though, FS... I don't know. I can't remember off the top of my head everything that's in FS2, to be honest, right now. Why are FM1 grade boundaries so high? Because it's easy. That is the little secret, isn't it? If you do the module that is actually, oh, we'll do a bit of F equals MA, we'll do some moments, oh, maybe some energy if we're feeling a bit saucy, everything turns out okay, then you just do it and it makes sense, and the grade boundaries are high because lots of people do well. So who else is around before we get going? PGF is dead though. No, property generator functions are amazing. They're so useful. But anyway, because all physics and further, possibly also that, right? Because there's a big overlap between physics and further mech, which means you're basically doubling up, so people do well, etc., etc. I wouldn't say they're sweats. Right, we are going to get going. So what are we covering today? So today and tomorrow we are on our 100% completely live open streams. Welcome everyone if you have not met me before. I feel there's a lot of people just from the main chat in at the moment from our main course, but I am Nick. I'm going to be taking you through the next couple of days. just for free. It's just completely, just you can come hang out, absolutely chill. This is me. Look, there's a lovely picture of me there. There you go. One of the assistant heads here at MyEdSpace. I have a master's in maths from a leading UK university, been doing it for a while. Fully qualified teacher, been teaching for about 15 years now. I need to update this slide every year. That makes me feel old. So you are in good hands. So what are we doing? Today we are mostly going to be looking at complex numbers, de Moivre's theorem. We're going to do some roots of polynomials, some series stuff with Maclaurin, method of differences. We'll do a little bit of polar coordinates, and then we'll wrap it all up with some first and second order differential equations, and everything that isn't in that big list of things I've said will be tomorrow in terms of the core pure. And then throughout the rest of the week, we will be going through the applied modules. So that is a thing. So if you are interested in doing the applied modules, your FS, your FM, that is part of the full paid Easter revision course. I'll talk some more about that as we go through. But basically, all the details, I will put a slide up later on to get you onto that if you aren't already. But that will give you access to all of the modules. You could even come do the ones that you're not interested in. Each module will also come with a workbook. It comes with an exam paper, but it also unlocks all the video solutions to the exam paper that you are getting for the core pure, and it gives you access to all the recordings from all the courses, because otherwise I think they're only live for an hour at the end of this. So that's all of that there for you. So Cube Core, you have Guy usually. Are you year 12 further maths, or do you do the normal one? You sneaked into my main session one, brilliant. So we're doing discrete, so it will be today and tomorrow are our core pure streams, and then for those that are on the full ERC course, it will be Thursday is further stats, Friday is further mech, Saturday will be FP1, and then Sunday will be D1. Further mech and further and decision will be done by Joe does maths and by Guy does maths. Right, let's get going. I think it's far enough time for us to go. Apologies, there's a little bit of light onto my green screen, but it's a beautiful day. It is a beautiful day with the sun streaming into my little studio. Oh, what is the hardest topic in CP1 and CP2? I don't know. Chat, tell me, what is the hardest topic in CP1 and CP2? Let's just get our banner down just for now, and let's get going. So what are complex numbers? You tell me, what are complex numbers? Let's start by solving our quadratic. Okay, and I'm going to be super special because I'm a super special kid, and I'm going to do it by completing the square, and you can't stop me from doing that. I am in charge. So there we go. So we end up with x minus 1 squared is -1. And this is where the issue is. We have something squared equals -1, which is an issue for the masses. It is an issue for normies. It is an issue for the majority of the population, but not for us. We do not mind. We go, there is a number. There is a number, I squared, which equals -1. This is a much nicer definition. I prefer this. This one is good. And this one is, I wouldn't say bad, but it is distinctly, oh, do you know what? It is distinctly mid. So what we're going to say is x minus 1 is plus or minus I. So x is 1 plus or minus I. Just making sure we've got our definitions. This is the real part. This is the imaginary part. All right. So hopefully so far so good, but covering our bases. That is what a complex number is. It has a real part. It has an imaginary part, which all has to do with this special number I. You're very lucky. For a while, we had to use J because physicists and engineers nabbed I for something else, but we get J again. It was given back to us very graciously. Right. Expand and simplify. Very, very simple. Once we get this idea, basically, I behaves like any surd, doesn't it? Just think of it as a surd. 2 times 3 is 6. We get a 3i. We get a minus 4i. And then we do get a plus 2. And in fact, let's write it out fully. Minus 2i squared. As this is being recorded, so for posterity, we have it. Right, so if we simplify this, what do we end up with? Boys and girls, just pop it in the chat for me. I don't want to be doing all the work all day. 8 minus I, very good. 8 minus I. Let's put some equal signs in here just because they are, in fact, equal. Beautiful. Well done, Ems. Well done. Yes. Okay. If you're thinking this is a very easy start, it's supposed to be. It's the first slide of 29 that we're going to be covering in the next 4 hours. Okay, but we need to get our basics sorted. Beautiful. Do let me know in the chat, boys and girls, if you can't read my handwriting, if you can't hear me, if you can't see me. All right. I know the camera is very flattering. You can't see just how many gray hairs I have, but you know, technology, old person, you never know. Just do let me know. Right. So if we want to simplify this one, we've done rationalizing the denominator. You know how to do that. So we're going to realize the denominator. We don't like complex numbers or imaginary numbers in the denominator. So what should I multiply the numerator and the denominator by? Complex conjugate. So what is the complex conjugate then? Yes, 9516. What a name. What is the complex conjugate? 3 minus... Oh, should I even write the correct question down? What if I write the correct question down? What do we think? Do you think that will be a shout? There we go. Come on, colours. Come on. There we go. 3 minus 2i. So the complex conjugate. Beautiful. Beautiful. Flip sign in front of imaginary part, Michael. Absolutely. Absolutal. All right. So this in blue is the complex conjugate of in red. But it's still just difference of two squares, right? Just like with rationalizing, it's just difference of two squares. Like I say again and again, I have some absolutely spiffing magic powers. But at the end of the day, right? At the end of the day, it's just absurd. So that's 8 minus I over 13 if you expand that, which is beautiful. Beautiful. That numerator is the answer for part B, then. It's almost as if I had that one sorted out. So just as a quick check, what is the complex conjugate of 2 plus 6i? And who can put in the chat for me, what is the symbol for conjugate? How do I write the, what's the mathematical notation symbol for the complex conjugate of something? What do I do to the something to show that it is complex conjugate? A star. Yeah, that's a good one. All right, star. A little star. You could also, some places do a bar on top of it. Some places will do a bar on top of it as well. I think at uni I used the bar, Z bar. So there we go. I'm much more of a Z bar kind of guy, but star is easier for us. So that will be 2 minus 6i. You are in the way, little thing. Right. Cool. We've warmed up. We're loosey-goosey. We've done 5 minutes of just general work with complex numbers. I don't think I'm going to be spending tons of time on just general complex number work. All right, but manipulating them, so on and so forth. We should be. If you've made it this far in the year, in year 13, doing further maths, I'm hoping you are very comfortable with this. Right, the diagram of Argand. All the man did is he said, I'm going to plot these on an axis. And funnily enough, we still use the notation. Real part is X, imaginary part is Y. So the axis is real part of Z and the Y-axis is the imaginary part of Z. All right. And we can start plotting complex numbers on it, right? That number there represents 3. Actually, I'm not sure I need a bracket. 3 plus 2i. It's absolutely beautiful. There we go. Look, and we'll do another one. We'll do another one. We'll do another one here. How about, I know. Oh, I did forget this. Hang on. Give me 1 second. Minus 3 plus I over there. Which, do you say I'm forgetting a square root? The note of the modulus of... Oh, yeah, I did. Do you know what? It's because I normally put the square. So I would argue that I normally put the square there, but you are absolutely right. Thank you. Thank you. Let's put that there. So can we label them in coordinates? I mean, we can, but we tend not to, all right? Because this is not a like, they are essentially, right? Functionally, we are using Cartesian coordinates, right? But we are representing complex numbers. It is much nicer to actually just write the complex number instead. All right, much, much nicer. So each complex number, if you think of it this way, and we will talk about polar coordinates later, all right? But you can express them in polar coordinates, much like you can express a point with Cartesian and polar. We can write these in terms of instead of having a real part and imaginary part, it can have a r, so it can have a modulus, all right, mod z, which is just root x squared, well, it's square root of x squared plus y squared. It's just Pythagoras. And we've got the argument here, r theta. When drawing loci, do you need to give the center and radius? Depends on the loci, but yes. All right. Everything needs to be properly labeled. All right. If you are asked to draw a loci, which will be a little bit later on, we do need to do that. Okay. And hopefully we've got all of this completely sorted out. So if I go x plus iy instead, and I label it in here, everything should be fairly self-explanatory in terms of where everything comes from. If this were to line up nicely for me, there we go. That's beautiful. That's beautiful. All right. Let's get a bit of color in here. That's y. That's x. And basically, after that, we're using SOHCAHTOA and Pythag. Is SHM in differential equations today or tomorrow, Pikachu? I'm afraid I can't remember off the top of my head. Are we covering all the CP1 and 2 chapters today? So it's just a mix, right? I haven't really separated them into Corpia 1, Corpia 2. I've very much gone for things that sort of go together. So that's why we're doing complex numbers and polar coordinates today. Series are something a little bit different. And then just, you know, because we have 8 hours revision split over 2 days, I put first and second. So I haven't split up all the differential equations necessarily in CP1, CP2. It's just the content, right? Right. So anyway, this slide is just here for us to make sure we've got everything labeled, but it should be fine, right? Tan of theta is opposite over adjacent, and so on and so forth. Practice paper that you've got today is everything. It's a combined everything. So the one that you've got today, it's not 2 papers. It's like 100 marks, so it's a bit longer than a normal paper is. Okay, but the idea is that it covers everything. Right. So anyway, we're going to make use of this, right? X is our cos theta, just SOHCAHTOA. Y is our sine theta, again, SOHCAHTOA, right? It's all there. Sine theta is y over r. Cos theta is x over r. Just always come back to this. If you find this bit a little bit tricksy, which again, I really don't think most of you will, okay, because of where we've got to in today. Even if you do AS further maths, really, this is our core concepts. We should be perfectly happy with that. Now, loci, funnily enough, let's show some loci. Now, what I do want to give this idea is this, right? If I go z minus x plus iy, and this is actually, let's go a plus ib. The really important thing is what this represents. And this basically represents, and again, I'm going to be a little bit sneaky, having told you earlier that I tend not to write these in coordinates, is what it really is the line is the complex number. Think of it as a vector almost that joins up a random point z with a, b. All right. And this is core to a lot of what we say, a lot of what we do. So we're saying basically we are thinking of this dotted line as a complex number itself. Just instead of starting at the origin, it is, you're thinking of it almost as a vector. All right. Is sort of what we're thinking here, right? This here is the vector almost that joins the point z to the point AB. I'm trying to be very visual here. It's not a vector. It is not, but it behaves in very similar ways, right? Vectors have direction and magnitude. We can think of complex numbers with direction and magnitude. So it's this big mishmash of everything together trying to be friends and make sense. So what is this? Can someone put this in? So it's a circle, center 1, 2, and radius 3. Does this mean that z could be anywhere on the circumference of the circle? Absolutely. So what we're saying here is the distance modulus. So this is a symbol for modulus, the length of this line that joins z to AB. So in this case here, it is, we've got the point 1, 2, right? We've got the point 1, 2, 1 plus 2i. Think of this as minus 1 plus 2i. So this is saying that that dotted line that joins z to 1 plus 2i has to be the length of it modulus. Okay, again here, our modulus is this radius, is the length, right? So the length of that line is set to 3. So let's see if I can do this. Let's see if I can do this half reasonably. So has to go to 4 there. Has to go to minus 2. Has to go up to 5. How's that looking? How's that looking? Bosh! There we go. There we go. Love it. Okay, so that's all it's saying, right? It's saying that if I take any point here on my circle, that's all this radius statement is saying. If I take any point, right, z could be there, z could be there. What this little dude here is saying, z minus 1 minus 2i, all right, is just the line joining up. Think of it as the complex number, the dotted line, whatever, however you visualize it, the vector, joining our random point z to 1 plus 2i. We're saying the length of that line is set to be 3. Le bosh indeed. Simples. If we understand what the language is saying, the rest of it is super duper simples. It is. It's super duper simples. You missed that circle to the exam. Yeah, I won't lie. It is kind of helpful. All right. But you know that sort of toolkit that we've been telling you to have for years and years. Kind of handy. The whole compass, protractor, etc. Now, what's B saying to me? So we're saying the argument. Now, remember, the argument is the angle that you make with the horizontal. Very important that. That is the angle you make with the horizontal. That's what we're saying. So what we're saying is that angle between z and minus, so remember, this is z minus 2 minus I. This minus is important, right? This minus is important. So let's go find the point minus 2 minus 1. So that is the point minus 2 minus I. And what we're saying is that if I take a point z and join it up with it, the angle that makes with the horizontal has to be pi over 6. Well, okay then. Well, okay. Now, let's see if I can do this. Beautiful. Boop. Because what we are saying here is that if I take any point z on this one, I'll do it in blue. So z could be there, z could be there, z could be there. What we're saying is that the angle that that line joining z with to over here, that angle there has to be pi over 6. The circle, say that again. So, Ash Gamer, how do you go from half line to Cartesian? Okay, that's an interesting question. That's one for in a second. Malik, the circle shouldn't be dotted as it's not in the... oh, I see what you mean. Yeah. So the beginning of it should be a little dot. I'm with you. Thank you. It's just to show the angle. Yes. Yeah, Simahar, like I hadn't got round to it, right? Give me a sec. Yeah. So absolutely. So the point itself there is not. Okay, so if z itself was minus 2 minus I, you will be at the same point. The line joining them doesn't exist. It's not actually... What is the argument of the point 0? It doesn't have one. The argument, the gradient is tan theta. Absolutely. Absolutely. Okay? Because the argument of 0, I think, is just undefined. The argument of 0 is undefined, I do believe. So isn't the angle it makes with the real axis also pi over 6, Dylan? Yes, it is, right? Just basic, right? If you go here, just basic parallel line theorems, absolutely. But the way I visualize it, I just think of it as with the horizontal, but it is essentially there. But I don't know, visually and in terms of how you draw it, you never draw it by measuring the angle with the real axis, right? With the x-axis, you will measure it from the horizontal from the point it starts at. So if that's how you're going to draw it, let's think of it that way, right? Why is the gradient tan theta? We are bordering here into the whole polar coordinates into Cartesian. So if we can hold off on that until later in the day, but that is absolutely true, right? If you think of this as the line y equals mx plus c almost, then m is here tan pi over 6. All right. What about drawing loci in set notation? It's all much of the same thing, right? It's all much of the same thing. Just in terms of complex numbers, the real thing to understand is the notation modulus and the notation argument. After that, we can talk some more about going from polar into Cartesian, set notation, all of that later on when we look at polar coordinates, right? But if you really wanted to, right, let's just take a little aside. How do I write this as a, how would I write this? Sorry, in Cartesians, right? How to do a half line. All you have to do is restrict the domain, right? You would just restrict the domain and say x is bigger than -2. Would say real part of x is bigger than -2. If you put that in your domain for your function, for your straight line, well, that means you are only starting from here. Or you could always put y greater than -1, right? Creating a half line is quite simple. You just have to change the domain. Let me just try something here, if I remember how it goes. What's the Desmos syntax? Yeah, so hang on, let me just show you this. Here we go. So if you want to do a half line on Desmos, all you have to do is put curly brackets, x is greater than 1, which funnily enough is your set notation. All right, and I'm just restricting the, it's just restricting the domain. That's all you have to do. Now, you finally got your protraction compass. Awesome. What an absolute legend. All right, but there we go. So this is the Desmos syntax. I think GeoGebra is very similar as well. All you have to do for a half line is do that one. Okay. But really what I want to focus on here, what I really want to focus on here is this idea of z minus a plus ib and what that represents. Once you've got that idea, the idea of an argument and a modulus, you're just saying, well, it's an angle, it's a distance. Apart from that, if you know your polar coordinate stuff, you know this as well. It's just a little bit of notation. How are we doing for time? It is 10:30. We're going to go for about an hour and a quarter, a little bit more, hour and 20 probably. Okay. And then we'll take a 10-minute break. Now, real talk. Let's go on to De Moivre's theorem. There is a lot to talk about today, right? There is a lot to talk about, which is why we are moving at quite a steady pace. All right. So we're going to talk about many things at the same time. If you want me to clarify something, you just need to holler in the chat. This is super important, right? This is why we are live and it's not just me talking for most of the day. It's all about what you want me to talk about. If you want me to go over a step again, if you want me to explain, do another example, you just need to holler. But funny enough, 8 hours even across 2 days to do all of Core Pure, it's a big ask. De Moivre jump scare, bah! Surprise De Moivre. We're going straight in, right? If we're going to talk about modulus arguments, which we are, okay, we're going to talk about De Moivre. So the first things first here is, if I was to take root 3 plus I, this cheeky, right, complex number here. So this is root 3, that's 1. Importantly, that has length 2, and this theta here is pi over 6. So the important thing here, if z is root 3 plus I can tell you that mod z is 2. And I can tell you that argument of z is pi over 6. Simples. All right, just a little bit of Pythagoras, a little bit of SOHCAHTOA. And importantly then, right, I can write z as 2 times cos pi over 6 plus I sine pi over 6. And that is super important. This is our modulus argument notation. This is the modulus argument notation. Is that diagram to scale? Look, you, shush. It's probably not super far off. Is it to scale, honestly? So Gabriel, what topic is this? This is our little intro into de Moivre's theorem, all about complex numbers. Because if I'm honest, the first 20 so minutes of what we talked about is our very basic complex numbers. It's really not the thing we need to spend time on. De Moivre and how we use complex numbers to do cool stuff is what we need. Now, what cher Monsieur de Moivre said, qu'est-ce qu'il a dit? He said, look, what happens is, I think de Moivre is French, so cue very, very bad and probably a little bit racist French accent. Neil doesn't rate de Moivres. Well, do you know what? That's Neil's prerogative. So what Monsieur de Moivre said is, look, it is easy. Huh? If you take a complex number and you take it to the power of n, you are multiplying the argument by n. And you go, ooh, very interesting. Very, very interesting. It is right here. And you go, oh, oui, oui, oui. And that is really cool. So if I want z cubed for number I, remember that is 2, that will be 2 cubed times cos pi over 6 plus I sine pi over 6 cubed. But Monsieur de Moivre says that is 8 times. And what de Moivre said is I can do that, that is cos of 3 times pi over 6 plus I sine 3 times pi over 6, which is, of course, 8 times cos pi over 2 plus I sine pi over 2. Well, cos pi over 2 is 0, sine pi over 2 is 1, so this should just be 8i if I'm not being silly. Malik got the same as me. Get in there. Le Bosch, indeed. So Ash Gamer, can we just use EI theta? It is the same thing. Again, all of this mishmash is in. This formulation is important though then when we start doing trig identities, which we will get onto. But yes, if we use, I mean, this is why I'm not proving it to you, or we'll talk about that a little bit later. But the idea is, of course, yes, that e to the I theta, that exponential notation does confirm it does the same thing, right? Whether, because you can prove this without e, without any Maclaurin series, anything. You can prove this just by induction if you really want to. Not the focus of today, all right, but sit down and do it. If you're bored and you don't have any friends, you can do it. And in fact, when we do cram course, I think I sit down and do it. I've done it on a video before, all right. But I'm not going to give the answer in E form. Your calculator can't work out e to the I theta. You need a better calculator. So z to the 8 is 2 to the power 8, and we're going to jump straight into this. This will become cos of 8 pi over 6 plus I sine of 8 pi over 6, thanks to Monsieur de Moivre. So what's that? 2 to the power 8. This is a big number. What's 2 to the power 8? 8 times 8, 64. 256? Is it 256? Oh, CG50. Look, I haven't even got to the CG50. Can you give your answer in E form, Pikachu? Not for this, dude, right? Not for 8i. If it comes out nicely, put it as 8i, right? Put it as 8i. So, 4 pi over 3 minus a half. Is that minus a half? And I think 4 pi over 3. No, minus root 3 over 2 and minus a half I. Is that right? No, other way round. Pi over 3 is big. Pi over 3 is big. So that's minus a half, and that's root 3 over 2i. Okay, and if you multiply that out, that's minus 128 minus 128 root 3i. Okay? There you go. I got you, Michael. I caught myself before I let anyone before anyone corrected me. Neil would say you've got a CG50. I do have a CG50, but I also have a noggin brain, right? Although here it took me a second, but I'm going to use my noggin brain. If anyone made a Nick out of like they will, right? Every year they end with a Nick out of context video, and you know the people in the nice white coats and the van and the padded room come and talk to me. Right, 2 to the 4. So z to the 4 is 2 to the 4 cos of 4 pi over 6 plus I sine 4 pi over 6. So 2 to the 4 is 16, and this is 2 pi over 3. So that will be minus a half plus root 3 over 2i. So I do believe that's minus 8 plus 8 root 3i. You think, yeah, I do sometimes freeze. All right, look, multitasking is difficult. All right, I can't think and breathe and move and talk at the same time. It's incredibly tricky. Yeah, just have a little loading symbol to pop up onto the screen. See if I can fix that for tomorrow's screen, for tomorrow's one. Okay. Mental maths is lacking. All right, then get your calculator out. Get your calculator out. I could, like, at some point I will make a mental maths mistake. You guys can correct me, right? It's just really basically what it comes down to is actually very fiddly for me to get the, look, I can get the calc up, not a problem. It's right here, but using the on-screen calculator is actually quite fiddly. So I will stay away from it for as long as I can, or I might just ask you. Liam, where's Nightbot? I don't know. I thought I turned Nightbot on, but Nightbot is not here. So, can I do an easier version, Gabriel? I won't lie to you, dude. Like, this is pretty much as easy as it gets. So, if you want to take powers of complex numbers, this is the process. You turn it into modulus argument form. Now, whether you write that in terms of the modulus and cos and sine, or you look at the exponential notation, which we'll get onto, that is completely up to you. Right? That is completely up to you. But at the end of the day, you will end up doing this maths, right? You will end up doing this maths. You will end up multiplying the argument by whatever the power is, and you will end up multiplying the modulus. Let's do another one. Let's do another one. So let's go, do you know what? I will just write it in modulus argument form already. Let me just check. So I will write this as 3e to the I, let's go pi over 4. So let's just talk about our modulus argument form. Where did I put this actually? Maybe I didn't. Maybe I didn't. Okay, so let's just talk about our modulus argument form. And it's up here, right? Very important. So if mod z is r and arg z is theta, you can write z is re to the I theta. And that is just true. E to the I theta is cos theta plus I sine theta. This is by, you can use it with power series, you can use Maclaurin series, all right? There's a bunch of different ways to prove it, but this little bit of notation here is rather key, I suppose, so let's mention it. So Michael, the integer in front is the modulus and the angle multiplied by I is the argument. Absolutely. Absolutely. So Liam, should we add the modulus to power of n? Well, I just haven't put a modulus in, right? Because the modulus is a number, is a number, is a number. So I never use it in here, really. And when we tend to use de Moivre's in this form, we tend to use R as 1. But yeah, it's in there, right? It's in there. It's just, that's not the difficult part. The difficult part is this, which is why I never write it in. That's it, right? The less I have to remember, the easier my life is. So, right, a number to a power is just a number to a power, not difficult. It is this bracket that is interesting. So whether you remember de Moivre's in this form or you write everything in this e to the I theta form, we can go z, I don't know, to the power of 4. So that becomes 3 to the 4 e to the I pi over 4 to the power of 4. So you can always remember de Moivre's this way using it, because power of a power, you multiply the powers, which is kind of nice. So that is going to be 81 times e to the I pi. But this is what I was saying, right? Whether you do it with exponentials or with full de Moivre's, at the end of the day, you need to go back to the idea that e to the I pi is cos pi plus I sine pi. There's nothing to be done about it. You have to go back to that idea. And it really is the same thing every single time. When you multiply complex numbers, you are going to multiply the arguments. You are going to multiply the moduli, and you're going to add the arguments. Okay, I'm building all of this into these ideas. Again, this is a quick Easter revision course. It's revision. All right, so there's a lot of stuff that we are going to sort of mention in passing as we move through. But if you want me to elaborate, I absolutely can. I think E is my favorite between all of those. E is just super cool. A number to a power is just a number to a power. What do you want from me, right? What do you even want from me? It absolutely is. It sounds dumb, but it absolutely is. Cos pi is -1, sine pi is 0, so this should come out as -81. All right, so Liam, yes, we are going to do some binomial expansions. That is absolutely part of what we're going to do. Brian, do we use this method as well for roots of unity? Yes, it's all the same. It's all coming. All right. Everything's like coming at me at once, because that's the thing, right? We introduced the Moivres, but it's like, but you can use it for this. You can use it for this. You can use it for this. And it all comes into this simple idea of how complex numbers interact when you multiply them. E is everywhere. E is in fact everywhere. What does the R mean? It is the modulus echo. So R represents the modulus. We come back to here, right? We use R for the modulus. It's the length, because basically it's polar coordinates. Think of it as the radius joining the origin with your complex number. Right, now you're just messing with me. S plus P plus IQ sequences, yes. So applications of de Moivre's. So here are the two main ones. Now this is a blank one, which I'm going to riff on. But it comes to this. There are two main ways of applying de Moivre's, okay? Yeah, just making sure I've got those lined up. And it boils down to how we apply this. So we're going to say Z is, if you just take a complex number that has modulus of 1. So this is why I tend not to use it, put it in, because we tend to do this an awful lot. So Z is cos theta plus I sine theta, which is e to the I theta. Okay, this is our core other definition. De Moivre said that Z to the n is cos n theta plus or plus I sine n theta. Perfect. Now, what I do want to mention is this. Z to the -1, right? Z to the -1, all right, becomes cos of minus theta plus I sine of minus theta, which is e to the minus I theta. That is just de Moivre's. But cos of negative theta is the same as cos theta, and sine of negative theta is negative sine theta. And this is another really important thing. This is another really important one for us to get down. This idea that e to the minus I theta is just minus I sine theta, which also tells me that this is Z star. It's only Z star because the modulus is 1. Be very careful with that, all right? Be very, very careful. This works because we are taking mod Z is equal to 1. We have decided that mod Z is going to be 1, okay? So what am I blathering on about? Well, it's this idea here. If this is true, then cos theta is Z plus Z to the minus 1 over 2. And then sine theta is equal to Z minus Z to the minus 1 over 2i by looking at these two things. And this is going to be key. So between this thing here and this thing here, we've got everything covered. Why do they look like... So there we go, right? Why do they look like hyperbolics? Well, because that's where it comes from. It's why they are hyperbolic trig functions, Ash Gamer, right? So we could also write this, remember, Z is cos theta is e to the I theta plus e to the minus I theta over 2. And sine theta is e to the I theta minus e to the minus I theta over 2i versus your actual hyperbolics, which is cosh x is e to the x plus e to the minus x over 2. Sine x is e to the x minus e to the minus x over 2. Why do they look like hyperbolics? Because this is sort of where hyperbolics come from. I say where it comes from. There's a lot of chicken and egg arguments in maths, right? But they come from because that's why they're hyperbolic trigs. That's why it's cosh x. All right? That's why it's cosh x. That's why it's sine x. It's why the hyperbolic functions behave in very similar ways to the trig functions, despite not being periodic, anything like that. But that's why you've got all those laws about the compound angle formulae for hyperbolics, things like that. It's because they follow that same structure of exponentials, which is also why E is my favorite one. So anyway, this is how we are going to use applications of de Moivre's theorem, because what's really cool is this, right? Is I could go cos to the n theta is z plus z to the minus 1 over 2 to the power of n. And what this enables me to do, this is basically what I'm getting to. This will enable me to go from something which is a power of cos, I can get it into something in terms of cos n theta. Same for powers of sine and so on and so forth. This approach over here in this corner is what will allow me to go from powers of trig functions into linear versions of trig functions, which, as someone said earlier, is super duper duper helpful for integration. Cube Core. We'll have a look at the textbook a little bit later. Not textbook, formula sheet later. Sorry, did someone put the loading screen up there for me? We'll have a look at that a little bit later. Also, if you sign up for our exam masterclass, I will provide you with a full booklet with all the formula you need, if they're in the formula booklet or not. But yeah, none of these really are in there, right? There you go, Penguin. Saying you somewhere that have that already done. Whereas this is also very useful. The standard one is very useful if I want to go the other way. So this is very good if I want to go from something like cos n theta back to something of the style cos to the power of n of theta. And I will show you examples of both of these over here. We're going to do 2 examples going each way there over here. All right, so we got that in a couple of slides, but really these are the main 2 things. The purple idea, which lets you go from a power to linear, and the orange one, which lets you go from linear to powers. We'll talk about the masterclass just before the break, if that's okay. MRJB8032, we'll have a little talk about that a little bit later. All right. Do not fear, I will tell you all about what we've got going on going into the exam masterclasses. But if you are doing applications of de Moivre's, it will come down to either what's in the purple one or what's in the yellow one. Once you've got those 2 ideas down pat, you should be okay. Okay, and it's all about which thing we're going to do a binomial expansion of, which we'll talk about in a sec. When is the next break? We'll take one at about, how about we do a little break just before 11:30 for 10 minutes just to refill waters. We'll do one about 11:20 in about half an hour, and then we'll break for a slightly longer one for lunch at about 12:30, and then we'll do a last hour and a half or something like that, hour and 10, getting us to the end of the day. So, Brian, how do you go from z to the -1 to this one? So I've got the breakdown up here. We got the breakdown up here, and it all comes down to de Moivre's theorem, right? If z is cos theta plus I sine theta, if I take a power of z, that power just gets tacked in front of the argument. All right, we had it up here, so it's just this with n is -1. It's just n is -1. So if you think of n as -1, it becomes cos of -1 theta plus I sine -1 theta. That's how that works. Okay, that's where we go from there to there. And then using our standard ideas of trigonometry, we know that cos of negative theta is cos theta, and sine of negative theta is negative sine theta. That's all it is. All right, very, very simple, basic applications of de Moivre's. All right, if you want the proof of de Moivre's, anything like that, that is something, I think I've got a video on it, but you can find separately. Okay, right. Let's start using de Moivre's. All of this, let's put it into action. Roots of unity. Now, this also works for roots of any complex number. Z to the 5 equals 1, find Z. Step 1, all right? Step 1, we're going to write the right-hand side in modulus argument form. Okay, we're going to write it in modulus argument / exponential form. Okay, so 1, right? If you just take the complex number 1, you could plot it if you really wanted to. The complex number 1, it is here. There is the complex number 1. Real part of Z. Look how cute my little argam diagram is. So you can very easily see that it has a modulus of 1 and it has an argument of 0. Right. Now, weirdly enough, I'm going to write it that way. So that is 1 times e to the 0 I. Okay? But here's the trick. Of course, because we are well cool, we is though, and we know about trig, of course, 0 is not the only argument. I could think of it as 0, but I could also think of it as 2 pi. I could also think of it as, if I was mildly insane, which I think we've already established is not a possibility that we can completely disregard, it could also be 4 pi. It could be 6 pi. So in fact, what we are going to do is when we write this thing as, and I'm keep the 0 in there just because it's universal, we can always add 2 pi onto our answers, right? We can always add 2 pi on. We can always add 2 pi onto it, okay? Next, we can take a power of 1 over n. Nice and chill. We can take a power of 1 over n. So in this case, z is going to be, and I'm really, really spelling it out for us here, right? I'm well aware that in reality, you wouldn't spell it out this much, but I'm really going for it. We're going to take the 5th power of all of this. Now, in our case, again, Nick's quote, power of a number is just power of a number. There we go. Nice and easy. That is 1 to the 1/5, which is just 1. But what do you do with power of a power? We're going to multiply them. And I've kept the 0 in there for long enough. It's going to disappear in a second. So what we actually get is that z is e to the 2k pi over 5. But the absolute essential thing when you are doing roots, when you are doing the roots, is this one. All right, that's the plus 2k pi. Whatever the original one is, it is whatever it is. I've kept it in as 0, right? If we did a different one, which I can always do another one a bit later if we have some time, Bro did not forget the I. Bro is checking that you're paying attention, EMS. All right. So there are actually 5 answers. We could get Z is e to the, well, e to the 0I. I'll leave it as that. E to the 2 pi over 5I. It could be e to the 4 pi over 5I. It could be e to the 6 pi over 5I. E to the 8 pi over 5I. And if I go one more, I loop back to here. 1, 2, 3, 4, 5 answers. So is the range theta between minus pi and pi? That one depends a little bit. Okay. Honestly, I know what you mean. We could have instead gone backwards. So we could, instead of those two, I could have gone e to the minus 2 pi over 5I, and I could have gone e to the minus 4 pi over 5I. That would be equivalent. I think it doesn't matter. Technically, between minus pi and pi is our principal argument. It is. All right, technically it is. I think you should be fine going from 0 to 2 pi. The W, okay, all right. Well, lots of questions here. Interesting ones. So, the one with the W EMS, I'll do that in for this one in a second. I think, yeah, I'll do that exact thing for the next part of this question. Don't you worry. Instead of adding 2k pi, could we just form a geometric series and multiply by the argument, which is what you're doing? Yeah, it is. And I'll show you geometrically why that is. All right, and we'll do that geometrically. But quite honestly, what it boils down to is simple trig, right? You've got all of these ideas of form a geometric series and why it's on the Argand diagram, and look at what it does using that. But fundamentally, all it is this idea that you've had all the way through, like to some extent, even GCSE, solving basic trig equations, sine theta equals a half. It's this idea that you've got so many options, you can just keep adding 2 pi ad nauseam, right? And it just simply boils down to that. It's no more complicated than that idea that you can always add 2 pi to an angle and get the same values of cos and sine. That's all it is. All right, there aren't infinite answers. Well, it depends, right? It depends how you view it. There are infinite values for the argument, but there are only 5 individual equivalent values of z, if that makes sense. So there are an infinite number of arguments that I can use. I could use 2 pi, I could use some more, right? You absolutely could. But they only end up generating 5 answers. So your answer should be either the top line or the bottom line, right? One of these two things. It's completely up to you. I find this one easier to not forget than these ones, and I get that nice progression. But these are my 5 answers. Now, in terms of complex numbers themselves, that is e, and that is cos of 2 pi over 5 plus I sine of 2 pi over 5, etc. This is just really horrible to write out, and I don't know what cos of 2 pi over 5 is. I think it might have a nice answer. What is? I'm in radians. Good. Cos of 2, and this is where we get into just how awkward this is for Nick to use. Yeah, it doesn't do anything nice, I don't think. All right, which is why we will tend to leave it in the exponential form. Yeah, we can do another example in a sec, right? But bearing in mind, yeah, we're okay for time. Now, geometrically, what this means is we've got one answer here. Now, if it's roots of unity, your answer will always be 1. And then if you are better than I am at divvying up something into 5, then please do help me out here. But all your answers, 1, 2, 3, Something like this, maybe. But the point is your answers will be evenly spread out. Now, this looks terrible, but that's because 1, 2. All right, they are evenly spread out every 2 pi over 5. And I know this is not to scale, not to scale. It should form a pentagon. I know it should form a pentagon. It is a shocking pentagon. Can you just use a rotation? All right, Marshall. Yes, you could use a rotation matrix, but now you're just showing off. It does kind of look like a square. All right, let's not judge my ability not to scale. Do you know what? I'm probably better off. Oh dear. So this is sort of an important idea. So we are going to do a couple more things on it, right? I am going to do a couple more things on it. But what I'm going to do is, just so that it looks vaguely okay. Just so it looks vaguely okay. If I do this, I can then move these around and try and make it look sort of like a proper pentagon. Something like this. That feels a little bit better. Feels a little bit better. Can you do an example where z is equal to a complex number? Absolutely, absolutely. And then I will show you how to muck about with some of the other bits and bobs. Okay, so let me just make a little bit more space. So what complex number shall we choose? What complex number shall we choose? Shall we do z to the 4 is equal to 3 minus 4i? Okay, so let's do z to the 4 is equal to 3 minus 4i. Now, really? No, I'm going to do something else. Tell you what, let's go back to... Let's do this one, root 3 plus I. Let's do root 3 plus I. How about we do that? Let's do root 3 plus I. Now, as we've already established, that is 2 cos 2 e to the I times pi over 6. But it is not just pi over 6. You can always add 2k pi to that. You can add 2k pi to that. Like I said, boys and girls, I haven't split this into day 1 core pure 1, day 2 core pure 2. Whilst we are mucking around with complex numbers, we're going to do all of complex numbers. All right, that is the plan here. So what do we do? I can take the 4th root. So that is 2 to the 1/4. And if I multiply all of that by 1/4, do you know what? We will end up with this. Now, 2 to the 1/4 is 2 to the 1/4. It's root 2. Right? It's square root of root 2. Ah, that's it. Okay, fine. That's pi over 24 plus k pi over 2. If we multiply that through. Okay, so my answers will be 2 to the quarter e to the I pi over 24. So that will have that is basically, remember, that is cos pi over 24 plus I sine pi over 24. Well, I'm taking a fourth power, MRJ, right? Unless I'm very much mistaken, the modulus of this is 2, right? So I need to take a fourth root. So I need to take the fourth root of 2 as well. Right? Is z to the 4. So it's the fourth root. Why do I divide by that? Why do I divide by a quarter? Because I need to undo a fourth root. You got me panicking, right? When I live stream, right, like little hiccups do happen, but do be just don't stress me out, right? It's this. I need to take the cos. So this is literally the definition. E to the I theta is cos theta plus I sine theta, right? That is just what it is. Again, because we're doing revision, we don't have time to delve into every single detail of this. All right, but it's what I was writing here. E to the I theta is cos theta plus I sine theta. You can prove it by Maclaurin series, a whole bunch of stuff. It's like Neil's, if you've done lessons with Neil, if you're here, you probably did the ones over the weekend. He's got that cool tattoo with what? E to the I pi over 2 plus 1 equals 0, because he's well cool. No, e to the I pi plus 1 equals 0. So I'm doing it, right? Bouncing around, trying to answer everyone's questions. So what happens to the pi over 2? I'm now going to start adding it on. So that's also 2 to the quarter e to the 13 pi over 24 if I add one of them on. And then it's really up to you. If you want your main one between, you could start subtracting it as well, or you could keep going. Up to you. Is that right? No, that is not correct. Minus 12, so it's minus 11, sorry. 11 pi over 24 and minus 23. And of course, I need to put some i's in here. There we go. So the main thing is, right, the real thing is if you have, where this comes from, right, is twofold. Is we use the Moivre's idea to say, well, if I take the fourth root, I can just divide the arguments by 4. That is our absolutely main thing, times a quarter. If I want to go from z to the 4 to z, I'm taking the fourth root, I'm taking a power of a quarter, and all that does is it multiplies the argument by a quarter. All right? But the crux of what we're doing here is z equals root 3 plus I is the fact that argument of z is pi over 6. Cool. But it's not just pi over 6. It's also 13 pi over 6. It's also 25 pi over 6. Or it could be negative 11 pi over 6. These are all the same angle. In terms of our description, in terms of this, these are all the same angle. They are. All I'm doing here is I'm adding 2 pi. I'm adding 2 pi. All right? I'm taking away 2 pi to get to that one. But these are all the same angles. So where I'm getting my 4 different roots from is the idea that when I take my 4 answers is when I take that fourth root, what I am doing is I am taking the fourth root of any one of these 4 values for the argument. Hi when you have a root, sorry, I'm right up in the screen. If a roots of unity question, say they give you a center and a vertex, you have to translate the center and point back to the origin before you start doing this. Well, I mean, not really. Like, oh, I see what you mean. I see what you mean. I mean, sure. So do you mean a question like, we're not going to cover every single possible question here, right? Let's just be absolutely clear. You mean something like this, say? Something like that? Because all you have to do is you do this and then just add on whatever complex numbers in there at the end. So essentially you are right. We just pretend we're at the origin, but I think you're overcomplicating it, right? If you're thinking like that, you are possibly overcomplicating it. All you need to do is undo the power of n. Well, that's all we're doing, right? When we go from here to here, all we're doing is taking the nth root of root 3 plus I. We say roots of unity, but we can do it with anything, right? Like we just have. And then at the end, much like, the very first question we did today, I undid the square root, then I added the 1. Absolutely same thing, right? You undo the nth root and then you add on what's left in the bracket. That's absolutely fine. Okay? The roots of unity do not necessarily equal 1. If it's roots of unity, 1 will be one of them because you always get that e to the 0 I. 1 will always be one of them. But then you get these other ones popping in that are split evenly around the circle. EMS Mon, yes. Let's find a little bit of space. So if I shrink all of this, oh dear, if I shrink this, like I say, this is putting us maybe a little bit behind, so we might need to speed up later. But this is an interesting question, so let's do it. All right, hopefully we have enough space down here. Okay. So let's say that z to the 5 equals 1. The main thing to write is this. Now, really, really important identity this is you can factorize out the 1. And what's left in here is z to the 4 plus z cubed plus z squared plus z to the 1. Plus 1. Okay? Now, what questions will do is they will say, let w equal to. Whether you do it with z, blah. All right, but this form of factorization is always true. So you can always make a little box for yourself. Z to the n minus 1 will always be equal to z minus 1 times z to the n minus 1, z to the n minus 2, all the way down to plus z plus 1. And this is the core idea that comes out of it. Okay? Now, what is interesting is we can start doing I've done a bunch of videos actually recently on TikTok and YouTube on this one. So let's say like a lot of these questions will use W, but this one is super cool. Brian, yeah. So like we start from Z to the 5 equals 1 and we get to this one. But what I want to show you is this next idea, which ties in with roots of polynomials. So we're going to jump back and forth a little bit. But if you have a look at this little cheeky chappy here, this is a polynomial. This is absolutely a polynomial. All right. Now, what this is saying is that if W is a solution, okay, if W is a solution, then you could say that the sum of all the W's, W1 plus W2 plus W3 plus W4 is equal to 1. Roots of unity. Or in this case, minus 1, in fact. Minus 1, sorry. All right, because what you could say is hadn't intended to talk in depth about this, but you could always write this as z minus e to the I 2 pi over 5 times z minus e to the 4 pi over 5i times Bosch times Bosch. Okay? So basically you can factorize it all out. But what's interesting when you look at this is if you look at the coefficient of z cubed using all the stuff that we're going to talk about in roots of polynomials, you can say that the sum of all of these roots but you can really start getting some interesting solutions. But this is what it boils down to. And after this, it's all about the individual question. But one thing you can start looking at, which again, we need to keep moving. But if you combine both of those and think about how they combine, well, that is just 2 cos of 2 pi over 5. And you can really start getting some nice little ideas about that one. And in the same way, you can combine these two to turn that into 2 cos of 4 pi over 5. So we are getting a little bit off piste here, but sorry, minus, I swear I've written that -1 and said it 14 times and just not there. So what we end up with, oh dear Lord. What we can end up with here is the idea that cos of 2 pi over 5 plus cos of 4 pi over 5 is equal to -1/2. And you've got all kinds of questions that will do that. But the key factorization is here. And then you use things you know about roots of polynomials, and then you can start using things you know about how causes and sines interact. Oh, look, guys, your names in the chat. Like, I've got people with weird numbers in there. So I see M's, I say EMS. Is there an exam question like this in a past paper? Oh, yeah, there are multiples like this. All right, there are multiples. Right, let's just keep moving because we spent quite a bit of time on this, a little bit of a sidetrack, and it's not part of our core ideas. Yeah, if you want to go more details about the roots of unity on the Argand diagram, again, 8 hours, there's only so much we can cover in all of it. All right. No, but it's worth the question. Just for this identity up here, it's always worth you asking about it. Right, now back to our proofs. Oh, Pikachu, no, I don't off the top of my head. I'm really sorry. Let's do 2 proofs. So we're going to go, this is what I was saying. We want to go from a power to something that is linear. All right, so I want to start with a power of cos and go to just linear functions of cos, cos 2 theta, cos 4 theta, something like that. What is the trick? We go back and we use the fact that cos theta is z plus z to the -1 over 2. If z is just e to the I theta, okay, which is cos theta plus I sine theta. Okay, that is the key idea that we're going to use here. So if we want cos to the power of 4, what I can do is I will do a binomial expansion with the z's. So that becomes 1 over 2 to the 4 times z to the 4 plus 4z squared plus 4 plus 6 even. There we go. And this is the trick. This is the trick. What I then do after my binomial expansion is I group the powers. See this bad boy here? See this bad boy here? if we combine all the different ways of doing the Moivre and I group it, what I'm actually going to do is I'm going to take one of these halves and I'm going to turn this into z to the 4 plus z to the minus 4 over 2 plus 4 times z to the 2 plus z to the minus 2 over 2 plus 6 over 2. So what I've done is I've taken one of those 2's. Instead of 2 to the 4, it's now 2 cubed. I've taken one of these in. Why is that helpful to me? Because that is 1/8 times z to the 4 plus z to the minus 4 over 2. That's cos 4 theta. Z to the 2 plus z to the minus 2 over 2. That is cos 2 theta plus 3, and we get our identity. How do I get negative powers? Ah, okay, right. So, if you really like, I'll do it vertically. Some people prefer it if I do it vertically. All right, and then I get z to the 4, z cubed, z squared, z to the 1, z to the 0. And then I'll get z to the minus 0, z to the minus 1, z to the minus 2, z to the minus 3, z to the minus 4. And if you look at how these combine, right, z to the minus 1 to the power of 4, z to the minus 1 cubed, z to the minus 1 squared, z3 times z minus 1 is z squared. But here, z to the 1 times z to the minus 3 is z to the minus 2. Okay. All right. So it's just that. Whoops. Easy peasy squeeze the lemon. That's where it comes from. Slurp, absolutely. Hang on. What are you talking about, Malik? I'm not Neil. I know I'm not Neil. I do not have the hair to be Neil. Right, now what if we want to go the other way around? What if we go the other way around? So I want to go from something linear to something looking like this. We do this. We use the fact that cos 4 theta plus I sine 4 theta is just cos theta plus I sine theta to the power of 4. Okay, so we are going the other way around. So we're going from power to linear. We're going to do a binomial expansions in terms of z's with a very particular z. Otherwise, I'm just going to use de Moivre's, and I use the binomial expansion on the de Moivre's. And then it's that easy. So that's cos to the 4 theta. Oh, well, it's that easy. What I always get wrong is keeping track of the i's when I expand the I sine theta. So that should be 4 cos cubed theta sine theta I. Then it becomes minus 6 cos squared theta sine squared theta. Then minus 4 cos theta sine cubed theta I, and then full circle plus sine to the 4 theta. Super easy. And then all we need to do is take the real parts are equal and the imaginary parts are equal. And then it's just tidying. After that, it's like you say, Richard, it's easy, but it is long. It is long and annoying. Not much we can do about it, but it is long and annoying. All right, so for example, if I take the imaginary parts, and this idea of comparing real and imaginary parts is fairly important. So that's 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. And really, after that, you know, it's all about tidying up. So for example, the cos cubed, what I'm going to do is I'm going to take out a 4 cos theta, and I'm left with a cos squared theta sine theta minus sine cubed theta. But of course, cos squared is just 1 minus sine squared theta. And as people have said in the chat, it's just tedious. So it comes in at 4 cos theta times sine theta minus 2 sine cubed theta. When taking the imaginary parts, you just ignore the I. Well, yeah, I mean, it's on both sides, right? There is an imaginary, get it? Essentially, you're saying that there's an I in all of those, but you could just divide both sides by I. You just divide both sides by I, right? That's it. See how bad you shorten cos to C and sine to S? Oh, yes, use nice capital ones if you're going to do that, like the CIS notation. I'm not a huge fan, mostly because my handwriting is pants and my S's look a lot like my fives. If you can tell the difference between your S's and your fives, yeah, you absolutely can. Instead of cos, write C. Instead of S, sine, write S. Absolutely fine. I tend to stay away from it. I have to write a little bit more, but at least I can read my own working. Brilliant. All right, just trying to catch up on what we're doing. Cube cross. Yeah, you got the loading symbol for me. Beautiful. Yeah, Liam, like we've said, it's absolutely fine. You just find the notation that works for you, so long as your final answer, you write it properly in terms of cos and sine, right? Your final answer needs to be in cos and sine. But again, make it work for you. This question I wouldn't, because we need to find the value of C. I've written a bunch of C's. The person marking your exam, so long as you are clear, your handwriting is okay, and it is consistent, they will figure it out. That's absolutely fine, right? At the end of the day, it's just working to get you to the answer. If you have clear working that gets you to the right answer, your own little quirks and idiosyncrasies and notations are absolutely fine. So A is 4, B is 1, C is -2, as Pikachu says. How many marks would this be? Yeah, like again, as you can tell, it's just not a thing I do, just because of my own personal handwriting. Writing C is cos theta, S is sine theta, but absolutely, it's a nice shortcut if it works for you. All right. How many marks would each of these be? 5 marks each? Yeah, they're not tricky. But the main thing is just having in your back pocket how to go from a power of cos or sine into something which is nice and linear. Great for integration, or how to go the other way around. This can be very useful for solving equations, for example. Powers are better, right? Because you've now got polynomials, much nicer to solve. So there we go. Again, we do not have time today to go through every single type of question, but I'm just trying to give you the main techniques that you are going to apply in different cases. After that, it's very case by case. That's why we've got the exam masterclass. We'll do a cram the night before. So between the two, we've got everything covered. Is there an easy way to remember? I mean, there's only 2 real cases, right? There's only 2 real cases. Go from power away, in which case you need to use this notation, these identities over here. I suppose I haven't been completely right. Cos n theta is z to the n plus z to the minus n over 2, with some very limited use of de Moivre's, and you can get the equivalent for sine as well. There's only 2 versions of it. Not everything needs a super cheeky way to remember it. You're not asked to remember a lot of stuff in maths, so just learn it. Right, it is 11:30. I was going to try and do this one before a break, but what I'm going to recommend is we've been going for an hour and a half. Let's take a 10-minute breather, boys and girls. We'll take a 10-minute breather. So go have a comfort break, go to the bathroom, fill up your water. What I'm going to say is I'm going to put up, all right, the QR code for the full East Revision course. So if you've just tuned in to hang out and do a bit maths with us, absolutely brilliant. If you're interested in going through the applied modules later on in the week from Thursday onwards, click this code. It will take you through the whole process of how to transfer from your free account right now to a full version. All right, how much it costs. But what it unlocks for you is it unlocks all of the applied modules, well, the one modules, so do be careful there, M1, S1, FP1, D1, which will be another full 4 hours on each one of them, a workbook, a full exam paper with worked solutions, as well as recordings for today, the recordings for tomorrow, which otherwise you won't have access to, and full recordings for all of those up until the exams. Just spam questions till you know it. Yeah, Krieger. All right. So I'm going to disappear for 10 minutes. You guys go chill for a little bit, and we will be back at 11:40, boys and girls. So I will see you in 10. Is it not public? No. See if I can change that. Thank you, boys and girls. I think that should change now. I'm glad you all waited. I'm glad you waited 90 minutes to tell me. The only difference is people wouldn't see us pop up on YouTube. I doubt we're going to go viral at the moment. We've got 70 viewers, but there we go. It is now unlisted. If you share the link with anyone that you know from your classes or anything like that, that you think might want to hang out and do some maths today, tomorrow, do just say the link with them. The sped up course, do you mean the exam masterclass? I will. Towards the end, I will talk about it. All right. Thank you, everyone. Thanks, cool kids. You got to keep me going. All right, this is a team effort. Right, 11:40. We will be back. Let's make Nick go away. Spooky Nick voice. And we're back. We are back. All right. Who is with me in the chat? Just trying to keep sure that my tech is all working. There we go. We are all here. We are ready to go. I've even treated myself to a little bit of soda right there in my classic Batman Forever mug from McDonald's back in the 90s. There we go. A classic bit of 90s memorabilia for you there. We each have our own stuff. 11:40. That's the time we said, and let's go. So next thing we're going to do is we are going to look at using the Moivre to get series values. Now, I've taken one example here. You need to be able to adapt to different ones, but they mostly boil down. Distracted by something in the chat. There we go. You need to look at what is going on from term to term. So you'll notice that we are multiplying by a half every time, and this is going up by theta every time. So what we're going to do is we are going to create a series that looks like this, C plus IS. Now I am going to use capital C and S, and this is sort of why I tend to stay away from it otherwise, because this is when I use it. And what it's going to be is it's going to be 1/2 cos theta plus I sine theta plus 1/4 cos 2 theta plus I sine 2 theta plus 1/8 cos 3 theta plus I sine 3 theta, and so on and so forth. If you're lucky, this is an infinite series. Most of the time it is infinite. Very occasionally it isn't, which is horrific. All right, but it doesn't really matter. It's much of a muchness. Now, this is where the exponential notation might be a little bit nicer for us, because that's e to the I theta plus 1/4 e to the I 2 theta plus 1/8 e to the I 3 theta plus etc. Because what we'll notice is we have a geometric series here, and every time we are multiplying each term by half e to the I theta, e to the I theta, 1/2 e to the I theta. Ishan, will this stream is available for about an hour, 2 hours after we finish, so into the afternoon. But if you want access to it between now and the exam, you will need to be on the full ERC course. Or if you're just a main student with us, if you're signed up to our main course, then you've got access to all of this anyway. So the idea is what we have here is we have a geometric series. So what we are looking to make is a geometric series whenever we have this. So this is why we are going to add stuff and we're going to compare and we are going to create our geometric series. Because what have we done is, in fact, if you look at just the imaginary parts, right, what I've called S is you will get the original series that we're looking for. But by adding in cos terms, we can now use our exponential, our de Moivre, however you want to think about it, to create this geometric series, which is beautiful. And this is an infinite sum. If it was a terminating sum, if it only went up to e to the 12 theta, you know the formula for a geometric series up to an nth term. You know that. 90% of the time, these questions are infinite. So that's why I've gone with this one. So my infinite series is, so this is a geometric series. First term is 1/2 e to the I theta, and my r is 1/2 e to the I theta. Will they always be the same? No, it's very much a case-by-case situation. You need to be able to deal with that. All right, but this is a standardish one. So absolutely. So this is going to be 1/2 e to the I theta over 1 minus 1/2 e to the I theta. Pikachu, I'm not sure we'll have time, right? If you put a pin in that, make yourself a little note, ask me at the end. If we have 10 minutes at the end, we'll come back and we'll do a non-infinite one, right? But they're just fairly messy. They're not harder per se, it's just you end up with a less fun. Basically, this expression here is less fun. The top is a lot less fun. The bottom, what we're going to do with the bottom doesn't really change. The bottom doesn't really change. All right, but what I am going to do, because I am lazy, is this. There we go. Now, this is a non-real number. This is a complex number. So we're going to multiply by the complex conjugate. Now, very importantly, this doesn't change. The only thing that changes when you want your complex conjugate is you put a minus on top of this. So again, let's keep going. If z is r e to the I theta, I think we already wrote this somewhere, but z star is r e to the minus I theta for all the reasons we've outlined above. So do be very careful about that. So what do we end up with? So the numerator becomes 2e to the I theta minus 1. All right, so you do not change that sign there. That is incredibly important. Bonjour, Mehmet. Ah! Bonjour, bonjour. So let's multiply this out. So 2 times 2 is 4 minus 2e to the I theta minus 2e to the minus I theta plus 1. Now, things to note down here, I've used this multiple times before, but ei to the theta, e to the minus I theta, go have a look here, right? We've used it there. It comes up time and time and time again. This is 2e to the I theta minus 1 over 5 minus 4 cos theta. Okay? We are using the fact that e to the I theta plus e to the minus I theta is equal to 2 cos theta. So we are using that. Absolutely standard, right? Absolutely standard down here in the denominator. Now the numerator itself, if I split that into real and imaginary parts, that is 2 cos theta minus 1 minus I sine theta over 5 minus, sorry, there's a 2 there as well, so that's minus 2i sine theta. There we go. And now all I need to do is look at the imaginary part. Now all we need to do is compare the real and the imaginary parts. Liam, if you did all of this in cos plus I sine, absolutely. If you want to convert here into cos plus I sine, you can. I would argue it just makes it fiddlier to work with, but absolutely you are 100% free to do that. It means you might be less likely to make the little whoopsie here for the multiplying by the conjugate. So that's also fine. So why can we assume it's I'm not assuming anything here at the start. I made it. All right, I didn't have a nice geometric series. My original thing in A is not a nice geometric series, but you know what? I used it as an ingredient in my C plus IS because I was well smart like that to make one. And it's largely the same thing every single time. If you have a series with a whole bunch of sines, you're going to add on the equivalent series with a whole bunch of causes. If you have one with causes, you'll add on I times the same thing with sines. It's very much the same thing. Why is there a minus? There isn't. Sorry, there isn't. There is no minus in front of it, M's. Soz. Do you know what? I'm going to go back to EMS. I prefer EMS. And there's nothing anyone can do about it. All right, but it's always the same idea. But if you want to do this with cos and sines, maybe you are less likely to make the mistake when getting rid of the complex numbers. Absolutely fine. So the cos, I made it. I put it in there. I decided to put it in there to make to be able to write these as the exponential form. I wanted the cos theta plus I sine theta. I wanted that. So I made it. I took the infinite series that I was asked to talk about and I used it as an ingredient for one that I knew was going to make e to the I theta, e to the I2 theta. And then at the end of that, very much like we have been doing, if I've got something that is real, that is complex, right? C is real, IS is imaginary, and I think the banner can go away. For complex numbers to be the same, their real parts have to be the same, their imaginary parts have to be the same. So in a second, we'll do the same thing. This C idea here is all the real parts, they have to be the same as well. So it's standard, right? Realize what we've done here, and this is the power of it, right? I'll just get super animated. We've said, square root minus 1 doesn't exist, and mathematicians went, but what if it does? What if we made a number? What if we said there was a number that I can square to minus 1? And everyone went, okay. By the way, trig. And everyone went, okay. And now what I've done is I've started with something that's completely real, that is completely legit, that exists. There is no need for any weird maths. Sine theta, sine 2 theta, sine 3 theta. Said, I'm going to bring in I. And everyone went, oh, okay. And some cool stuff happens. And at the end, I say, yeah, but I's a bit funky. I'm going to get rid of it. Okay, so this idea of like comparing real parts and comparing imaginary parts is very, very important in maths because I unlocks all of this cool de Moivre stuff, all of that, and we bring it in and we go, yeah, but the real parts have to be equal and the imaginary parts have to be equal. It's very, very, very common. Because what I can say now is my S, which is my sine series here, my S, my sine series, which is a half sine theta plus a quarter sine 2 theta, etc., plus 1/8 sine 3 theta. That's all the imaginary parts. Well, I've just said actually by using what I know about geometric series, that's got to be 2 sine theta over 5 minus 4 cos theta, and that's just the truth. And for part B, I can now, I've done all of this already. Kian, right, remember e to the I theta is cos theta plus I sine theta. That's all I've done, right? So that is times 2 is 2 cos theta plus 2I sine theta. And all I did is I grouped the real bits and I grouped the imaginary bits. That's all. So C, which is the one that I added in, right? The C is the one that I absolutely pulled out of my bottom. And I went, I'm going to put this one in. Why? Well, because it needs a little bit of cause, it needs a little bit of sel, a little bit of poivre. I know what I'm doing. I'm going to put lots of butter in this and it will be delicious, right? This ingredient that I put in to make it super tasty and do the stuff I wanted it to do. Oh, I put a little slurry to make the gravy thicken. I put it in there because I wanted it to do a thing. And I'm allowed to do that because you can't stop me because I'm bigger than you, right? So that thing there, if you look at the real parts of my geometric result, and there we get it. Okay, so it's just the real parts. Okay, that's all it is. Brilliant, Alice. I'm glad you're enjoying it. Okay, but that's all it is. Now, whether it's this or some other question, this is the idea. As soon as you get these long series, and again, we just need to keep moving just because I'm conscious of time. It could be that you have some n's in here. If it's up to the power of n or power of 8, you might need to change, oh, sorry, this part here to fit with that. But the general idea of then getting rid of the complex numbers in the denominator and then having to play around with the top a bit, that's universal. Liam, who came up with complex numbers first? Do you know what? I don't know off the top of my head. You might have to have a look at that for me. Right, roots of polynomials. This one we're going straight into a question, nice and easy, super simples. That's what we're going to go to. Okay, is it Descartes? Awesome. Now, first thing we're going to do is I'm going to take my cubic here and I'm going to divide it all by 5. That's all I ever do. I don't remember it in any other way. Now, with roots, you have to realize that if this cubic has 3 roots, and it does have 3 roots, they might not all be real, but it does have 3 roots. The polynomial button. Nah, leave the polynomial button alone. Plus, you can't do this kind of stuff on it. Now, important results from this. If you are to expand this out, oh, that's p over 5x squared. That might be useful. Okay, so this tells me if you expand this out and compare coefficients, that alpha plus beta plus gamma is negative p over 5. You could also show that alpha beta plus alpha gamma plus beta gamma is equal to negative 3. And alpha beta gamma is negative q over 3. Just expand this out and compare everything out. Vietta's formula be like, look what you need to mimic a fraction of my power. Yeah, sure. Yeah, it's like, hold my beer, I've got this. What's funky though, right? If you go, I can use Vietta's formula to solve an equation, you just end up back at the cubic formula or the quadratic formula. It's kind of funky. But anyway, these are our standard ideas. I won't lie to you. I never remember if it's a plus or a minus. I literally, every question, because it changes whether or not it's an even power or an odd power, which is horrible, right? So what I do literally every time is I write this out for myself, x minus alpha, x minus beta, x minus gamma, and then I try and expand it. Now, I've been doing this a while, so I can expand it in my head. You might not be able to, right? But of course, that is x cubed. And then you get minus alpha plus beta plus gamma x squared, etc. But legitimately, I never remember these. I do this and I expand it. Yes, Black Ninja, good spot. I divided by 5 precisely so that I could just have x cubed, so I can just compare these directly. That's why I did that. Okay. Oh, apologies. Need to blow my nose quickly. Hang on. So, is it always plus minus? So it will always be alternating. It will always be alternating. Okay, we've got minuses because of the actual signs in front of these, but oh, yeah, we've got sound. It will always be alternating. Now, is it always minus b over a, c over a, minus d over a? For a cubic, yes, but what if there was a quartic? What if? Now, it does tend to be cubics. I am aware that these questions do always tend to be cubics, but as a general rule of thumb, right? What if it was a quartic? What if it was a quintic? Power 4, power 5, then it swaps. So you can remember them, right? Absolutely. If that works for you, absolutely. Basically, I don't like remembering things by heart. I don't like doing it. Never have. It's why I've done maths, physics, stuff like that, right? And not history. So this is largely what we're going to do. Okay. So you are given that alpha squared plus beta squared plus gamma squared. So these sorts of questions, what they do is they test your algebra, funnily enough. Should be Q, it should be Q over 5. Thank you. Yep, and it should be Q over 5. Don't know where, oh, it came because I was looking at that one. Thank you. Good spot. Right. Basically, what some of this comes down to is, can you expand this? Can you expand that? Now, it works exactly the way you think it should. You get all the squares and you get 2 lots of the double formulae. Alpha, beta, beta, gamma, alpha, gamma. Now, what's handy about this is I know that that is minus p over 5 squared. Now, we are told that alpha squared plus beta squared plus gamma squared is 22. But basically, once you've got this, it's all about algebraic manipulation, and that's it. Right? That's just it. Just do it. So, and then 2 times all of that, but that is minus 3. So that tells me that p squared over 25 is equal to, I want to say 16. So p squared is 400. So p is 20. Oh, when they are cubed, right? I'm not going to sit here and give you the cubed formula. The cube one, you can look it up, is just awful. It is just awful. Tell you what, maybe I will, but I will let's finish this question, and then I'm going to corner off this bit up here to do the cubed thing for you. Now, a lot of people that comment on the videos I've done when I've done questions with cubes, they've just said memorize it. Is it worth memorizing expansions? Well, yes, this one is worth memorizing, but you'll notice it's just the logical next step of just alpha plus beta all squared, right? It's just the logical next bit of that one. So that one's not too bad to remember at all. It just makes sense. Right. Does look like 4 times infinity. So let's see what Q is, but 1 over alpha plus 1 over beta plus 1 over gamma. Well, if we make that into a common denominator, that's beta gamma plus alpha beta plus alpha, no, sorry. Let's do it in order, plus alpha gamma plus alpha beta over alpha beta gamma. And we are told that that is equal to 23 over 5. Why 23 over 5? Couldn't tell you. Right, well, beta, all of those double products is minus 3. Alpha beta gamma is minus q over 5. And that is going to be equal to 23 over 5. Now, all we need to do now is deal with that. All we need to do now is deal with that. So let's continue it up here. So that is 15 over q is 23 over 5. So q is 75 over 23. 75 over 23. Nice. Okay. Now find the value of alpha minus 2, beta minus 2, gamma minus 2. A bunch of things you could do, but really, if you just expand it, that's alpha beta gamma minus 2 times alpha beta plus beta gamma plus alpha gamma plus 4 times alpha plus beta plus gamma minus 8. But yeah, actually, there's a numbering issue here. Hang on. There's a numbering issue there. Wouldn't that be if you got marks for just a statement? Right, but really what you need to do for these questions is essentially practice your expansions. Like, it sounds unsatisfying, but you need to be quick about these expansions. So alpha, beta, gamma is minus q over 5, so that's minus 25 over 23. That becomes a plus 6. The sum of them is minus p over 5, so minus 4. That's minus 16 minus 8. Right, alpha plus beta plus gamma, we now know that that is minus 4. We now know that that is minus 25 over 23. And we just sub them in. Is it 15? Oh yeah, 15. Soz. Look at that. Everyone looking after me. That is just horrific. Ain't no one want to figure that one out. Whack it into a calculator if you have to. I'm not doing that right now. Sure. Minus 439 over 23. I mean, that's 3 different answers so far in the chat, boys and girls, which is not reassuring at all, but there we go. Right, very quickly. Alpha plus beta plus gamma cubed. Right, let's see if I can remember how this works. We are gonna get gamma cubed. Honestly, I think it's better. It's not pleasant, is what I'm trying to say, right? It is not pleasant at all. All right, it is not a particularly nice set of anything. And you can do this multiple ways. Right? And then you want to start doing some stuff here. It's really, stop telling me I'm slurping. Has cubed ever come up? It has come up. It has come up. Basically, what I'm going to say is you need to play around with this or go look up and memorize the formula. I'm not just going to dump them on the screen for you, but there are like things you can look up for. The grid method for cubic, because the common items line up. Yeah, probably actually. Probably it has come up. All right, but what it comes down to is you need to group these up. And again, I'm very conscious of time. if I remember correctly, we need to do plus 3 alpha beta gamma minus 3 alpha beta gamma. We can come back to it a little bit later, and I'll try and get the full formula for you. I didn't have them ready at the top of my head, apologies. But that's the general idea if you want to derive them from scratch or you learn them. So yeah, you can figure out alpha cubed plus beta cubed plus gamma cubed. That is the whole idea. All right, but we're going to keep moving. I'll come back to it. We'll do a, we're going to take a break at about 12:40, 12:45 for about 20 minutes for lunch, and then we'll push on to the end. All right. Dylan, is it easier to remember? Yeah, but like it comes up so unoften. But then again, yeah, it depends how much you want to be sitting down doing this sort of algebra as you go through. Because what you'll notice here is I've got alpha squared betas. I've got alpha squared betas here. I've got alpha squared gammas, and I should have some other alpha squared gammas here. And you'll quickly see how this is going to come about. All right, you'll very quickly see how this comes about. There should be another one. Yeah, there's going to be a whole bunch of them. All right, but I'll finish this off at the end if we have time. Okay. Yeah. Siri very kindly putting that in the chat for us. All right, all right, all right, all right. Okay, so if you start collecting these terms, right? If you start collecting these terms, you will see that you can actually create from this thing that you end up with alpha cubed plus beta cubed plus gamma cubed plus 3 times alpha plus beta plus gamma times alpha beta, beta gamma, alpha gamma minus 3 alpha beta gamma. Sorry, that's not the tidiest ever, but that is the formula here. And that was equal to our alpha plus beta plus gamma cubed. So if you are interested in this, that's where it's all going to come from. Okay. Is part D different from finding a cubic with roots? Not really, no. So if we start doing this for all of them, you will end up with the coefficients for a cubic that has roots shifted by 2. And you can play around with that in different questions as well. But given that we don't know what the roots are, and I just want the value of this, then nice and easy, I just go, just expand it all. I don't know the name, if I'm honest. Not everything needs to have a name, right? Vietta's formulas, etc. I won't be. I will be honest with you. I never remember the names of all of these things. I just know what the things are. All right. Proof by induction. Again, we're just going to do a couple of examples of proof by induction. I'm going to leave the roots of polynomial for now, so long as you've got this as your basis point, and then the understanding of you're going to do a lot of algebra, we're probably fine. So we've got a summation proof by induction, a matrix proof by induction. I wasn't gonna because they're fairly straightforward, but we can always look at it later. So 5 to the n minus 1 is divisible by 4. So let's prove this by induction. So step 1, we're going to check n equals 0. 5 to the 0 minus 1 is 4. Bosh, bosh, divisible by 4. Okay. Number 2, we're going to assume that 5 to the k minus 1 is divisible by 4. So it's 4, I don't know, 4m? 4m? Sure. Sure. So now we have a look at 5 to the k plus 1 minus 1. Why 0 instead of 1? Oh, we could... Sorry. It is 1. It is 1. You'll notice I even put the number for 1, right? It is 1. You'll notice I even did it for n is 1. Thank you, Ishan. That's method of differences, Pikachu. That's coming up. Now, the trick for this one is what we really want to know is like, okay, if the kth term is a multiple of 4, what about the k plus 1th term? So the trick here for divisibility is to rearrange this into 5 to the k is 4m plus 1. because I can write this as 5 times 5 to the k minus 1. And I'm allowed to do that because I'm the boss. And then I can use my induction step. Okay, but this is the key. Whenever you're doing divisibility stuff with powers like this idea of taking a 5 out of this term is very, very common. So that is 20m plus 5 minus 1, which is 20m plus 4, which is 4 times 5m plus 1, which is divisible by 4. So you put in your conclusion, put it in the chat for me. What should the conclusion read? What should the conclusion read? Again, boys and girls, we do not have time over the next few days for me to do an example of every single type of question. If you have a look at this, you go through the exam paper, you come back to do the cram with me and the exam masterclass, you will see between all of them, I think we cover everything. What's the conclusion? Type that in. Cordelia, perfect. Nice and concise. It's true for n equals 1, and if it's true, you might want an if in there, Cordelia. So if it is true for n equals k plus... Oh, no, that's fine. I've just had the whole sentence. And it's true for n equals k plus 1, given that it's true for n equals k. So it's true for all n, not quite for all n. Not quite for all n. I think some of the others have put that in there. Shruti's got it in there. It's not true for all n. Some internet strangers got it in there. It's true for all n greater than or equal to 1. Remember, this is why I checked it for 0, but sometimes it doesn't work for 0. Because if we did it with 0, we get 0, and technically 0 is divisible by 4, but 0 is weird, right? But think of dominoes, right? Our first case was n is 1. If it's true for n is 1, it's true for n is 2. Because if we know it's true for k, it's true for k plus 1. So if it's true for n, for 1, it's true for 2. It's true for 2, 2 for 3. So it's not true for all n. It's true for all... Did you put all integers? And even then, no, not integers. You could put natural numbers. Integers can be negative. We have not shown this for negatives. Okay? So not integers. Careful. Integers are negative. So if you say positive integers, good. Positive integers, absolutely. If you said positive integers, I wasn't but loads of you were brilliant. You put it in the chat. I didn't necessarily see all of it. You go natural numbers. Yes, Joan has put that in there as well. I just literally will put all n greater than or equal to 1. All right, much like, okay, but do be careful. If you say integers, that does include negatives. Now, summation, very similar. All right, very similar. We're going to check n equals to 1. So we're going to do the sum from 1 to 1 of k times 2 to the k. That is 1 times 2 to the 1, that is 2. And that is in fact equal to 1 minus 1 times 2 to the 1 plus 2. Okay, so it's true for n equals 1. It is true for n equals 1. Now we need to do our induction step. So we assume that is true for n equals... Now, unfortunately, we've already got a k in here. So, I don't know. Let's go n equals r. So what we're going to do now is we're going to take the sum up to r plus 1, which is the r plus 1th term plus the old one. Right? This is my induction step. Now what we can do is take out a 2 to the r plus 1. Which is 2 to the r plus 1 times 2r plus 2. Now look out for this. Again, you get a lot of these questions where you have to muck about with the powers, right? So that is 2 to the r plus 2 and times by r. Now we do need to write this out very explicitly. R is r plus 1 minus 1. And that is r plus 1 plus 1 plus 2. All right. So you'll notice that I've really tried r here to really emphasize the r plus 1. Sorry. There we go. I really tried to emphasize where the r plus 1 rocks up. Is 0 in the natural numbers? Yes, it is. So I suppose, yeah, if you go belongs to it, no one would ping you for that. Can you split into 4 times? Yep, that is also a way to do it. It's a little bit more convoluted, Ranks. You can also do that. All right, you could also do that. I'll put that in blue as an option. You could do that first one as 5 to the, sorry. Yeah, we'll do it this one. 4 times 5 to the k plus 5 to the k. Take away 1. That is divisible by 4. That is divisible by 4. Yeah, absolutely. This is a little bit more algebraic, a little bit more mechanical. This is a little bit more vibey. It's very nice as well. It's also very nice. This idea of splitting it is not for everyone though, right? Not everyone likes doing that little split. This one is a bit more, I rearrange, I plug in. A little bit more plug and play, but I get your vibe. I get your vibe. Yeah. Okay, and then conclusion here. So which step to? So the step is really, the real induction step here is I'm going to split that into the r plus 1th term and then the sum up to r. That's the real induction step here, right? My sum from 1 to r plus 1, I split it into the sum up to r, which is here, right? The sum up to r, which is here by the induction step, right? Which is the induction step, and then the r plus 1th term. After that, it's just algebra. It's just trying to make it look the same. Ishan, no, the cram and exam masterclass are not free, I'm afraid. They are not. Okay, but that's the step. So with summation, that's very much the step we're going to take. All right, with summation, you just stop the sum at r and then whack on the r plus 1th term, or the k up to k and k plus 1, depending on the letters being used. For divisibility, it's more like this. For a lot of the other ones, these are the ones that tend to be a little bit more difficult. All the other ones do with matrices, anything like that, they tend to be fairly straightforward. Right, standard series summation. I'm afraid we're really going to have to motor now, boys and girls. Very simple. You need to know these. Are they in the formula booklet? We'll have a look at the end. But really, just know them. The more you know, the less. I know I've said many times, try not to remember too much. But I think someone said it in the chat. If you do enough of these questions, you will learn them. If you do enough of them, what I really like is the r cubed one is just the r1 squared. Then all we need to do, right? All we need to do is expand this one. So that is 4r squared minus 4r plus 1, which you can split. You can split into 4 times the sum of r squared. I need my other hand. Minus 4 times the sum of r plus the sum of 1. So that's 4/6 n plus 1 2n plus 1 minus 4 over 2 n plus 1 plus n. do you need a specific solution for the proof? And if so, what is it? What do you mean by that? Thank you, CubeCore. Very nice. I'm not sure I understand the question there, Echo. And unfortunately, right, what we might do is I'm actually going to multiply both sides by 3. All right, I find this a little bit easier. If I multiply both sides by 3, I don't have as many fractions to work with, and I can then divide by 3 at the end. Hopefully no one's going to hate me for this. I mean, you can expand, you can then tidy up. What I suggest is have a little look at what they're giving you. So they've got an n factorized out. So what I'm going to do is I'm going to factorize out an n. And hope that the rest works out. There's always a little clue in the answer. There's always a little clue in the answer. And again, all I've done is I've multiplied both sides by 3 because I didn't want that fraction. It's this LD interview question, I wish. All right, and you can also see there's a divide by 3 there, which is a nice little clue. 4n squared, 2, 3, that's 6n there. That's a plus 2. Minus 6n minus 6 plus 3. And I think we are getting there because the n's cancel out. And that is 3 times our thing. So 4 before, do we need a specific solution for the proof? So this is the specific formula, right? I've made it look exactly like what I wanted, just instead of n, I've got n plus 1, or r, I've got r plus 1. Then you put your conclusion as people have been putting. Okay, so do not be afraid when you're doing this, A, to have a little peek at what you need to show to know what you might want to be factorizing out, what you might want to be doing. So they factorized out an n, I factorized out an n. They told me the whole thing's going to be over 3. Tell you what if I times everything by 3, get rid of my fractions, and I'll divide at the end. That's a nice little sneak. That's a nice little sneak to avoid working with fractions too much. No one likes a fraction. Better than a decimal, but no one desperately wants to do too many fractions. We're going to keep moving, otherwise there is no way we're getting to the end of today. Method of differences, also known as, do you know your log rules and can you do partial fractions? See you guys if you're off. Again, if you are on the normal course, this is all recorded. If you aren't on our regular courses, but you are signed up to the full ERC paid for course, you have access to all the recordings. Otherwise, it will be available for a couple of hours this afternoon. Right. Basically, can you do partial fractions? So 1 over r squared plus r, that is 1 over r times r plus 1. So quick partial fractions, All right, very quick partial fractions, whatever your preferred way to get partial fractions is. Because then the sum from 1 to n of 1 over r squared plus r is the sum from 1 to n of 1 over r minus 1 over r plus 1. And what I always say is write out a few. Hopefully that's what you've been told as well. So we're going to plug in r is 1, plug in r is 2, plug in r is 4, plug in r is 5. Sorry, r is 3, r is 4. Okay? Now, because what you'll see is stuff will begin to cancel. Now, what I like to know is if I stop at 5, what's my last one? So if I stop at 4, I get a 1/5. If I was to stop at 6, I would get that. So if I went all the way to n, that would cancel, that would cancel, that would cancel. So what am I left with? I am left with 1 minus 1 over n plus 1. And then you just need to tidy that up. which is n over n plus 1, by the power of algebra. Yay, Dylan, love it. Okay, never overcomplicate. Just write out enough terms till you can see the pattern. It's that simple, right? Just write out enough terms till you can see the pattern. It's absolutely beautiful. Now, same with Lunds. Do you know your Lund rules? I did it in one step. I'm a maths teacher. I've got a maths degree, right? I have ways to do partial fractions. Here's a nice, if you want to know my way to do partial fractions, I'll give it to you very, very quickly. What you do, if I want the coefficient of r, cover it up, make that 0, so r is 0. So I cover it up and I replace r on the left-hand side with 0. 1 over 1 is 1. If I want to know the coefficient of r plus 1, I'm going to cover up r plus 1 and then plug in the value of r. That would make r plus 1 0. So that would be minus 1. 1 over minus 1 is minus 1. Bear in mind, this only works as long as you don't have repeated roots, you don't have quadratics, anything like that. So long as it's a nice linear one. Of course, Neil's got a name for it, the big toe method. Love it. So ln r plus 2. I think it's how Neil hires people. I won't lie to you. He makes us do a question with luns, and so long as we say it properly, we're hired. So ln of r plus 2 minus ln r. Yeah, that method is great so long as it's powers, like it's not repeated, it's not quadratic, anything like that. It works very, very nicely. So ln of r plus 2 minus ln r. So that's what we get. Like I say, do you know your rules of luns? So my sum of ln r plus 2 minus ln r, we're going from r equals 1 to n. Let's put it in a bit. So we'll put in 1. So ln 3 minus ln 1. Let's put in ln 4 minus ln 2. Ln 5 minus ln 3, ln 6 minus ln 4. So let's stop there for a second and see what has cancelled out. That has cancelled out. That has cancelled out. So this is the pattern we're going to have. So what you can see is if you just put in 4 or 5 lines and see what cancels out, it will tell you how far down you need to go. So in fact, if I go up to n, that will be ln n plus 2 minus ln n, and then ln n plus 1 minus ln n minus 1. Because if you compare this, right, we will have those cancel out and those cancel out, essentially. So you can replicate the pattern at the bottom. So what do we end up with here? We end up with ln n plus 1 plus ln n plus 2 minus ln 2, which is ln n plus 1 n plus 2 over 2. I love the fact that you guys are so chill that Nightbot doesn't have to do anything and it just occasionally tells us to like and subscribe. I love it. Where's that ln 1 gone? Why have I ignored the ln 1? Ln 1 is 0, absolutely. Cube core, you're driving me insane. Slurp. Ems, are you going to write anything down today? If that's to me, I've been writing a lot. Okay, but this is the idea. So do algebra, whether it's partial fractions, rules of Lens, whatever it is, to turn your, it needs to have a difference is what I'm trying to say, right? The big boy words are not coming, but you need, funny enough, to use a method of differences, you need to create a difference. All right, funny enough, we might not be surprised. Could you do n plus 1 after? No, Zachary, no, because we are summing up to n. All right, we are summing up to n. So this is why when I stopped at 4, I was very clear to myself that this is n is 1, n is 2, n is 3, n is 4. So if I stop at 4, that is the term that goes away. So we are summing up to n. So we need to stop at n. All right, we need n as our last line. N, funnily enough, as our last line. Okay, so we cannot, instead of doing the previous one, do the next one. Right, polar coordinates. Very, very simple. Well, simple-ish. Very, very similar to what we were doing earlier with complex numbers. We're going to get a little bit into polar coordinates, and then we will take a little break for lunch. The idea, of course, being that instead of expressing this in terms of x and y, we're going to go in terms of r and theta. All right. So a few extra things to put in here is that x would be r cos theta and y would be r sine theta. After that, it's up to you. What do we need to be able to do? I'm going to do some integration, right? We're going to do a quick sketch and we're going to do an integration. You also probably want to do a little bit of differentiation, but a lot of it is very, very simple, right? So let's say, what could we might want to do? So yeah, if you want to sketch the CG50, I'm going to be shilling that massively. I will show you, but that might be for after lunch. R equals cos theta, for example. Now that is a curve. What is the curve? R equals cos theta. We'll do sketching. But the real thing that we want to be able to do is we want to be able to go from xy to r theta and vice versa. So here's my little trick. Here's my little trick. If you want to get from xy, from r and theta to xy, r is not fun. Cos theta is not fun. Here's my little trick. If you want to do from one to the other, is multiply everything by r. Okay, this is a very common trick. If you multiply everything by r, you can then use all of this to get what you want. So r squared is x squared plus y squared. R cos theta is x. Oh, how are you the only person that's shouted that? That is horrific. That's an auto DQ. I might just have to go, I don't know, slam my hand in a door for that one. Okay, so if you want to go from r theta to xy, this is generally the trick that you're looking for. This is generally the trick that you're looking for, is multiplying through by r. All right. So r equals cos theta, it actually turns out is x minus a half squared plus y squared is equal to a quarter, if I remember correctly. So in fact, the graph r equals cos theta, if you look at this, is in fact a circle, center 1/2 0, radius a half. All right, but generally in polar coordinates, you need to be able to go from r thetas to xy's or xy's to r thetas. Sure, why not? You need to be able to sketch, you need to be able to integrate. We might want to differentiate, but again, differentiation is really not that tricky, right? But it does come out a little bit messy. You can also think of it as it's a form of parametric equations. Okay, you can think of it this way as well. So let's go back to my little graph here, right? R equals cos theta. Remember, x is r cos theta, y is r sine theta. But if I tell you that on this specific graph, for example, on this specific graph, say you know that r is cos theta, well, in fact, x is equal to cos squared theta, y is equal to sine squared theta, right? If we take the graph, if we take the curve, let's make that clear, r equals cos theta, right? I'm taking this one particular one, r equals cos theta, as our example. You can go from Cartesian to polars, polars to Cartesian, using all of these formulas. If you want to go the other way around, I would always suggest trying to create r squareds and r cos, r sine. Okay? once you've got this notion straight, we can get rid of the r. Well, this is just parametric equations. So dy by dx is dy by d theta over dx by d theta. Everything that we already have is completely legit. How did I get sine? Oh, sorry. I got carried away, didn't I? I got carried away. It's cos theta sine theta. Thank you. Cos theta sine theta. And you can also start mucking about with this, right? Using some double angle formulas, things like that. All right. But by and large, it's after you've got that straight. This is why I don't have an entire slide on differentiation, because if you realize that if you take x is r cos theta, y is r sine theta, plug in your function, you can then get this out. In a more general sense, if you've got the curve r is f of theta, then x becomes f of theta cos theta, y becomes f of theta sine theta up here, right? R cos theta, r sine theta. And after that, you can then muck about. Okay. Again, we are getting a little tight on time, so we're not going to be able to do full-on examples of everything. But like most things in maths, differentiation is a lot easier than integration. And you've spent a bunch of time doing parametric differentiation, doing tangents in one way, tangents in the other way. You've spent a whole load of time doing that in normal maths. So go back and check on that. Right, it is 12:40. I think now, before we go into graph sketching, where basically we're going to cheat and use a graphical calculator, then we're going to do a bit of integration. We're going to do some Maclaurin series quickly, which is just knowing, and then we're on to our differential equations. We might need to carry some of this over to tomorrow. We'll see. We're going up to slide 23. So hopefully we'll have time in the last hour. And then we'll finish off. I'll quickly talk to you about, again, the modules options and about our exam masterclasses coming up. So it is 12:40, my lovelies. I reckon I'm going to give us 20 minutes for a quick break, for a quick bit of lunch. So we'll be back at 1 o'clock. Liam, knowledge decay, just do maths. Like anyone that ever asks us, if you ask any maths teacher, how should I revise for my maths exam? We are all desperately exasperated and desperately tired of saying the same thing, which is do math, do questions, right? How do I remember this formula? Well, use it, right? Don't, like, flashcards are nice, but just sit down with a stack of past papers. I love doing the MyEdSpace past papers. By the way, the solutions to about 50% of them are on one of my social media channels, right? Nick Does Maths on TikTok, or MyEdSpace Maths on TikTok, or YouTube. A whole bunch of them are on there. Use the MyEdSpace papers. Go find different spec papers. It doesn't matter. Maths is maths is maths. For Core Pure, at least, all the specs are roughly the same. So the Core Pure for AQA, Edexcel, OCR-A, OCR-B is 90 to 95% the same. Just do maths. The MyEdSpace papers get real tricky. For Core Pure, we're looking at FP1, FP2. For FP1, you're looking at going into FP3. Like, his ones are very aligned with the old Modulus spec, so it's a little bit trickier, but it doesn't matter. Maths is maths is maths is maths. So Liam, that's the thing, but that's why if you grind over 2 weeks, right, 3 weeks a topic, and then do none of it over 4 or 5 months, it will decay. You need to be doing everything all the time. So that's why I always say, when you get to this point in the year, you shouldn't be doing 2 hours of the same topic. Really, what you want to be doing is half an hour of a topic and then an hour and a half of everything, right? Then you do another topic for half an hour, and then you do another hour and a half of everything plus the topic you've just practiced, right? You need your brain to be able to recall it all, because as you can see today, right, all the complex number stuff in the Argand diagram is very similar to the polar coordinates, similar to this, is similar to that. All right. The old spec papers for Edexcel is actually a little bit trickier, but I do think PMT has some of the old specs. But the actual exam board websites, Edexcel is a little bit trickier to navigate. I won't fib, but it might be on the Edexcel website. Otherwise, PMT, I think, has the legacy specs. Right. Back at 1 o'clock, boys and girls. Back at 1 o'clock. Nick out. This is the voice of Nick. I am here. 1 minute. Yeah, a little minute behind. Apologies, boys and girls. Oh, I didn't leave the sign up QR code because I'm very, very bad. What I'm going to ask you to do, though, before we crack on, could you just take a little second, please, to drop us a review on Trustpilot? Just scan the QR code. Tell us how much you're enjoying today. Maybe not say that Nick was 1 minute late. That's terrible. Tut, 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 tut. But if you want to just take a second to give us like an honest review, 3 stars, 4 stars, -2 stars, it matters not, so long as you are honest. It helps us out a little bit and helps other people, I don't know, consider us for Nick buffering for their revision. So let's get going. What do we want to do with polar coordinates? We are going to do some sketching. Now, honestly, one of these is super easy to do. One of these sketches is super easy to do, right? And it is R is 2. R is 2, super simple. What kind of shape has a constant radius? It is a circle. Ash Gamer, how do you know them? You learn them. Right, so the different shapes for a cardioid, if A is bigger than like 3 and 2, how does that compare? Is there a dimple? Is there not a dimple? Right, all of that, like the dipole cardioid, etc. Like you just have to sit down and learn them, right? Go through the textbook is what I would suggest. They have a list of, and all the ones they highlight. But really, like if you're doing further maths, especially as if you're doing further stats, investing in a grown-up calculator like this is absolutely a must, I would say. So how to plot. We go into graph. We will go delete everything I've got, and you can change the type, which is pretty cool. So I can go delete, yeah. So I can change the type of the graph. Is it worth buying a CG50? Yes, harder to do now. They've gone onto the CG100. I've played around with it a little bit. It's quite hard for me to get on the screen for you. But you might be able to get one for cheap. Some schools might get them in, but I think it's really good. So we go type and we're going to go R equals. All right. So again, you just go type and it's R equals. Okay. Interestingly, there we go. So for example, the second one was just R is 2, and we can just verify for ourselves that that should come out as a circle. It does not look like a circle. Why? Because the axes are all over the place. So general use of one of these. And you know what? We might, is that big enough? Can you see what we're doing? Hopefully you can. If we go V window over here, you could put it back to your initial settings and see what happens. And there we go. You could also go zoom, which is now there is an auto zoom on this, which does do some interesting stuff. I would just go V window initial, and then you can move around from there. So that's where that is for you. Right, so let's put the first one in. Make sure you're in radians. 3 plus 2 cos. Now, don't bother with these. I need to make sure I can see what you're seeing. Don't bother with these ones here. Whenever you want an x, a theta, a t, we're going to use this button on the calculator right there. And it will figure out which one you need. So there we go. So we've got our cardioid. Well, no, it's not cardioid. I can't remember what it's called, but there we go. We've got our sort of, it's not a full loop. We do have that dimple coming in. Okay, so we can start sketching this. Mark Scheme can't pin you, Liam. It can't. If they want you to sketch it, now, obviously, you need to know what you're looking out for. So when I started looking at 3 plus 2 cos theta, the main thing for me is, does it dimple or does it loop the loop on itself, right? Those are the two main things. Now, again, I never particularly remember which way around it goes. Why? Because that's just the way it is. But the calculator here helps me out massively. So I know it's going to come through here. It should. Now, you do want to be able to figure out where the maximums and minimums are. Cos, if cos is between -1 and 1, so at furthest it'll be at 5, at smallest it will be at 1, so that's why we're at -1 there. And it looks like it's coming through around there. We've got our little dimple like this. All right, And we do want to figure out properly where it goes through here. So let's, it should be 3 and minus 3, in fact. Okay, so at this point here, this is theta is pi over 2, and we'll get r is 3, bomb. Here, theta is 3 pi over 2, r is 3, bomb. Okay, and so on and so forth. Yes, that is awful. Label the intersection. So there we go. Oh, this one here, I haven't done it for the circle, have I? 2, 2, minus 2. Does it have to be to scale? No. Okay. Does it go to scale? No. Now again, if yours comes out not quite like that, you can go zoom, we can go out. All right, and then if I press, there we go. Oh, that's probably a bit too much. You could also go zoom auto and see what it does. There we go. But again, it mucks about with that. Yeah. What's that do? Interesting. There's all things you can play with, right? Once you've gone this. If you go trig, that's not great. You can go standard. What's that do? Minus 10 to 10. Right? Sometimes you just have to sit down and play. It looks like a wonky potato. Yeah. Right. Find the value of theta where they intersect. So already looking at this, it should be the value of theta where they intersect should be somewhere between. It looks like it should be somewhere between pi over 2 and pi. So what do? Well, we're going to make the curves equal. That this happens when they have the same r. All right, so this is what we need to do. Find the value where they intersect. They have to have the same value of r. So this will give me cos theta is -1/2, which is theta is, I want to say 2 pi over 3. Or secondary solution 4 pi over 3. Done. And again, that sort of looks about right. And this idea of it being symmetrical, 2 pi over 3, 4 pi over 3, that's lovely. Again, if you want to take the value between minus pi and pi, you can if you want to. I've just grown into 0 to 2 pi an awful lot. Okay, but for sketching them, really, my honest to God's advice at this point is if you can source a graphical calculator, it solves so much heartache, so much of it. You don't have to remember the things and you only ever get judged on producing the correct things. Now, look at my wonky potato. My wonky potato is a crime against math sketching, but does it have the right idea? It's looping round, and really the behavior you are looking at is here. So whilst, like I said, you do need to know what behavior you're looking out for. Does it loop through? Does it come back on itself? The graphical calculator will give you the answer to that and you can replicate it. XY for values of theta. You can always try that, I suppose. How do we draw C1 without a calculator? Right. So if I really want to do without a calculator, I start by looking at 4 particular values of theta. Just start with the obvious ones. Theta, pi over 2, pi, 3 pi over 2. So in our case here, we got r was 5, we got r was 3, we got r was 1, and we got r was 3. So at the very least, and you probably want to go to 2 pi as well. You also then want to look, is r negative? All right, because remember, if r is negative, you flip it back on itself. So for example, if C1 was r is 2 plus 3 cos theta, this is where it starts looping because r becomes negative. All right, so that also works. But then you just become loop de loop. So here I know that 2 cos theta will decrease up to pi over 2. It will then decrease again, and then it will start increasing. So that gives me a good idea. Now, the fact that it's not pointy here, how do we know that? That's a little bit trickier, but it gives you a good start. Are there any labels for the axes? Oh my lords. All right. Now, like I said, differentiation, so long as you remember this stuff here, I'm not going to go into any detail on it because it's just parametric differentiation. Let's do integration. But again, integration is actually relatively easy because we are just doing polar integration. Whoa, 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 whoa. It's not X and Y. It depends, right? What I have drawn here are absolutely valid X and Y axis. If you were to draw this properly, fully polar, what you would do is you would not have that, you would not have that, you would not have that, and you would have the origin here, right? If you are doing a proper polar sketch, the only line you have here is theta is 0. That's all you have. Okay, if we were doing a full-on proper polar sketch, okay, that's what you would have. So that is what we call the initial line. I wouldn't stress about it too much. Okay, you use whatever they tell you. You use whatever they would tell you in the exam. Quite honestly, I think a lot of times they will provide some axes for you for it. Okay, but ideally you do the initial line. But what I will say is I personally never sketch using the initial line. I think of it in terms of X coordinates and Y coordinates, quite frankly. So what you might see in some of the stuff I do is you might see a dotted Y axis appear. All right. Right. Now, polar integration. And again, I am putting in a Y axis. Leave me alone. All right. It helps visualize what we're doing. And the idea is this. Is we are going to use the fact that a small bit of area is 1/2 r squared d theta. A small bit of area is 1/2 r squared d theta. Okay? Area of a sector. This is just the area of a sector, BT dubs, by the way. All right? And you've done that in normal maths. So what do we want? Find the area enclosed between the curves C1 and C2. So if we want to do that, oh, mine just looks shocking, you know. Mine just looks shocking. So hang on a minute. Hang on a minute. Let's see if we can do this any better. There we go. Right. Just trying to make this a little bit neater for us. If you're wondering what it is I'm doing right now. There we go. So there are our two curves, much, much nicer. See, my way of formulating this leads to slightly leads to some slight confusion. So this is what I mean. So what are we going to do? The first thing we are going to do is we are going to find the area for the big curve. All right, we're going to find the area for the big curve. Now, it's nice and symmetrical. It's nice and symmetrical. So what we might even do, what might we do instead? Maybe. What we might do instead is only do half of it. All right, so what we might do instead is only half of it. Either way, we know that that is theta is 2 pi over 3. So what I want to do is I want to integrate 1/2 0 to 2 pi over 3. All right, and it's r squared, 3 plus 2 cos theta squared d theta. It's not the world's funnest integral to do, but it's one that comes up time and time again. Okay, because of course we know, and this is the thing that you're going to be using this so many times. 2 cos squared minus 1 is cos 2 theta. So this becomes 1/2 the integral between 0 and 2 pi over 3. 9 plus 12 cos theta plus 2 cos 2 theta plus 2 d theta. How do we know it's 2 pi over 3? It's the same curves as previous question. Yeah. So that double angle, we're going to use time and time again. Be ready to use it, right? This is one of the main types of curves you get given in polar coordinates. It's one of the main ones you're going to have to integrate. So you just want to be able to do it. All right. So we end up with 1/2 Bosch 11 theta plus 12 sine theta. Oh, my big fat noggin is in the way. So that is 1/2 of 22 pi over 3 plus 12 times root 3 over 2. Yeah, people are like, yeah, because of the 4, right? Because of the 4. Sine of 4 pi over 3. Yeah, it should be minus sine of pi over 3, so we should be okay there. So that is 11 pi over 3 plus 11 root 3 over 4. Why can we not equate them? Why can we not equate? What would equating them give you? With basically polar integration, you can't just do the difference between the two of them and square them. It's not, you can't. It just doesn't work the same way. So really what you want to do is you need to go back to basics when you're finding the area between two curves. So at the moment, what I've got here is the nice yellow one in theory, unless I've mucked up in my integral, in which case, please do tell me. In which case, please do tell me. But this is what I am getting. Again, nice thing about the CG50 is that you can check these things, right? You can go 1/2, and then we're going to go options. I've done a video on how to use the CG50, by the way. Just going to keep plugging my own stuff here. Oh, no. Hang on. Now, one thing to do, please. For some reason, it will carry that through. So you have to put yourself back in Cartesians, I think. There we go. That worked. We're going from 0. And yes, this is why we don't use it that much when we're doing live lessons. And then I'm going to do all of this. Then when I look back up at the chat, you'll be telling me where I went wrong. Yes, smashed it. Right. So that's 1/2 of it. That's absolutely fine. But what we do need to do is we need to take away that circly bit. But that's fine. That's just a sector of a circle, right? 1/2 times r squared times 2 pi over 3, which is 4 pi over 3. So what's left for me to do is I will take my yellow area, take away my green area, and then I will double it. So that is 14 pi over 3 plus 11 root 3 over 2. Can I change in the calculator settings? Almost certainly. Ah, yeah, if I just go, yeah. There we go. Thank you. For some reason, when you change into polar in the graph, it sticks that way for the whole calculator. So you have to tell it that you're back in there, which is a real pain. It's a real pain. Isn't it the yellow area times by 2? No, it's not, because at no point in that yellow area did I take that circle into consideration. So the bit that I want, the bit that I wanted, oh dear, that's aggressive. I'm not sure that's what we wanted in life. Okay, I see how it is. I see how it is. I see how it is. How do you like me now? So we wanted the red bit, right? So we wanted the red bit. To find the red bit, I do the yellow bit minus the green bit. So I want the bit enclosed by the two curves, right? Which is, if we only do half of it, let's just stick to half of it, because then we just multiply it up at the end, right? If I only want half of it, I want the bit in red. Okay, because that's enclosed by the two curves. Look, honestly, I formulated this question, probably not my best, but if you look at the two curves, you've got the curve there, you've got the other one there. So this is what we're looking at the area of, right? This is the area that we're looking for. Okay, that's the bit that we wanted. Yeah, like, don't get me wrong, what is ideal here, but I didn't draw the picture, is it's labeled R, right? Cube core, what's wrong? Oh, 11 root 3 plus 11 pi over 3 plus 11 root 3 over 4. Yes, for half of it. Absolutely. Where did the triangle come from? Because I'm looking where it's enclosed, right? So you want, remember, the limits you are doing is in sectors. So very important, this one, is to understand. Very important is to understand what is going on. So when we integrate in Cartesian, we integrate vertically, right? When you're integrating in Cartesian coordinates, you're doing a whole bunch of rectangles. You're doing a whole bunch of rectangles in Cartesian. Okay? You are adding up a whole bunch of rectangles. Okay? That's why. When we're doing in polars, we're not. We are adding up a whole bunch of sectors like this, radiuses. So when I start adding them up and I want the area between them, it goes like this up to where they intersect. We will finish it if we run over a little bit. Okay, so it's diagonal for polar. That's why. Okay, the area of the circle is in green. Sarah, how did I know is that one? Because I wrote the question. I wrote the question and I wrote it poorly. Don't worry, your exam questions will have a nice diagram with a nice big R labeled on it, right? Something like that. That's how that works. Okay, I just wrote this. I didn't have the diagram. It made sense in my head. Okay, but you don't have to worry about that. Right. Maclaurin's expansions, very nice and simple. F of x is approximately f of 0 plus f dashed of 0 x plus f double dashed of 0 x squared over 2 plus f triple dashed at 0 x cubed over 3 factorial. Basically, this whole question about Maclaurin is, can you differentiate? If the answer is yes, you're fine. If the answer is no, you're less fine. But learn cos x. But that's all it is, right? F dashed becomes sine x over cos x, also known, by the way, as cot x. F double dashed then becomes minus cos x squared x. We want the first 4 terms, so I'm going to want f triple dashed of x. It is tan, silly man. Silly man, thank you. We are reaching hour 4, and my brain is not braining quite as good as it was going. So f triple dashed is 2 sec x times the derivative of sec x, which is sec x tan x. So that is 2 sec squared x tan x. I'm just going to put the actual first 4 terms, not the first 4 non-zero terms. So f of x is roughly I give up, boys and girls. I give up. There you go. We want f of 0, which will come out as 0. F dashed of 0. Oh no, which is 0x. That's unfortunate. Oh, but we do get a minus x squared over 2, and then we do get a plus 0. Now, this is just an unfortunate question. Ideally, you would have the first 4 non-zero, but I'm just going to leave it as is. And if you're ever unsure, you can grab your calculator or, right, depending on how fortunate you are with your access to graphing software at any given time. And in fact, again, the Maclaurin series only really works for quite small values of x. We've only got 1 non-zero term, so it's not a great approximation, but actually it's not terrible, right? The 2 graphs match quite nicely. Oh, I need to get the chat back. Right, number B. We're not going to keep differentiating it for days until I get 4 non-zero terms. Can you do that on a CG50? Yeah, like legit. Yeah, sure. Like, boom, 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 boom. You just go, boop, graph. Just delete the formula there. We don't want that one. It'll be a pain. Let's delete that one. It'll be a pain. And we just go ln cos x. And we'll go minus x squared over 2. It's a little bit less facetious than Desmos, actually. And then up to you, really. Zoom in on our point. Zoom in on that point. But you get the gist. You can see that it does fit quite nicely. All right. Can we use the booklet for B? So that is also very, very true. But let's just have a little look-see at what's easiest for us here. E to the 2x sine x, f dashed. Yeah, it's a product rule. 2e to the 2x, keep the sine x, differentiate the sine x, keep the other one. Normally, much nicer to then factorize. Okay. F double dashed, differentiate that one, keep this one, plus keep that one, differentiate that one. Again, I highly recommend factorizing every time. 4 sine x, that is 3 sine x, 2 cos x. We'll see how well this turns out. And we'll go to our third derivative. Very rarely do you need to go beyond the third derivative. I know, hang on, 6 minus 4, 2 sine x, 8 cos x. I think that's 11 cos x. Do check me, please. Okay, so Ash Gamer, the idea of writing them both in their polynomial form and expanding is not terrible, but it does have its downsides as well, all right, which I will mention. That's why this question is here. It is doable, but it's not my favorite. So f of x is roughly equal to this at 0 is 0. This at 0 is 1. This at 0 is 4. This at 0 is 11. So according to me, which I am not feeling super confident about, I won't fib, let's just see what this does. And if you look at, see me, you know what, let's just bring it up. So you could probably figure out geographically in my office where the screen with Desmos is. And now for the bitter disappointment of something that's gone wrong. Oh, not bad. Oh, actually, check that out. Woo! Now, what I will say is you could absolutely, right? So e to the 2x, if you are confident in expanding these, and sine x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. The only issue with this is what you are coming down to at this point is mass expansion, right? And it's not awful, right? It's 1 times x is x. And then if you want the x squared, it's 2x times x. So that's actually not too bad. Oh, maybe it's not too bad in this case, right? It's not too bad. It's just there's a lot of cases where I would feel a lot less happy. For the x cubed, there's 1 there and there's 1 there. So that would be what? Minus x cubed over 6 plus 2x cubed. So yeah, overall it's not too bad. It's not too bad, but like it's a lot of expanding. I suppose that's a lot of differentiating. So horses for courses. Horses for courses, I suppose, but either way. All right, you get the right answer. I mean, if you want to know the different breed that we are, Nightbot has not had to do anything. Right, on to differential equations. Let's see what we can get done in half an hour. If we need to move some into tomorrow, I think I'd rather move some topics into tomorrow and then overrun tomorrow. What's the trick here? What do I need to do, my lovelies? What do we need to do? So first of all, that's x squared plus 1 over x dy dx plus 2y. This is not separable. This is not separable at all. This is an integrating factor. Now, to get the integrating factor, what we're going to do is we want dy dx by itself. Okay, dividing by x squared plus 1. Why do I want dy dx by itself? Because this bad boy here is going to help me get my integrating factor. So I'll do that in purple. My integrating factor, I need to first integrate 2x over x squared plus 1 dx, which is, of course, ln of x squared plus 1. Your basic integration needs to be hot. You need to be on top of it. You cannot be struggling with these integrals, right? You get so few marks, right? This will not be that many marks for this step here. It's like, yeah, you're doing further maths. Of course you can integrate 2x over x squared plus 1, right? So my integrating factor is e to the that, e to the ln x squared plus 1. So it's just x squared plus 1. Cool. So let's multiply all of this then by x squared plus 1. Sometimes you might just spot what the integrating factor is, if I'm honest with you, right? You might just spot what you can make happen. So all of this to get back to the fact that x squared plus 1 dy dx plus 2xy is 2 times x squared plus 1 squared. Oh, hang on. There's an x here as well. There we go. I lost an x on the right-hand side. I saw it before you told me. I'd lost a little x on the right-hand side. I knew I had to because I had the same thing on the right-hand side there as there, right? There's always little clues. And the key thing is this here, of course, on the right-hand side is a product rule. dy, that's the derivative of x squared plus 1y. Okay, so now all we need to do is integrate the right-hand side. So I get x squared plus 1y is the integral of, and I'm going to expand this, ain't no one got time for that. So that's 2x to the 5 plus 4x to the 3 plus 2x dx. Yeah. Now we're not going to worry about the plus c yet. It's nice to know, chat, that you are not going to let any mistake go by. No, I don't think I've done. No, right-hand side is. No, I think we're okay. Cotillia, we good? Oh, I see what you mean. I could have done it that way around. Yeah. I see. Yeah. Probably nicer to do it that way around. Yeah. So it's also that. Very nicely done. Plus a constant. Now, what I would do always is find the constant as early as you can, unless you've got lns. So y is 1 when x is 1. So 2 times 1 is, I will use that one. Good spot, guys. Bit embarrassed I didn't spot that, actually. Bit embarrassed I didn't spot that, but there we go. My way, guys, was simply to expand and then integrate. So I expanded and integrated, but for whatever reason, I didn't immediately spot that I had a reverse chain rule. It happens. It happens. No one's perfect. If you really want, you can do that way. Are we lagging? Let me just check. What is the internet saying? Stream health. Stream says it's healthy. Stream says it's healthy on my side. I don't know. Stream says we're healthy on my side. Get Desmos back up. Right. I think I get C as minus 2 over 3. So we should end up with y is that. Well, CubeCore, I think the stream just hates me. Let's try again. The stream is healthy. I don't get why you multiplied it by x. Here, right? I wanted that to disappear right at the beginning. Because we want the dy dx by itself. I'm loving it. Chat is on it, top of it, explaining stuff to each other. I love it. Look, we've been fine all morning. My internet's been fine. YouTube says that everything's fine. And if YouTube says everything is fine, you're wrong and I'm right. Do I need to go chat? Look, all I'm saying is I've got top speed fiber, and I doubt that my 4-year-old watching Octonauts is a problem. Okay, but that's the idea, right? Integrating factor, you all spotted that. You need to integrate the right-hand side. Do try and be more switched on than I was and spot any small chain rules. Okay, we're all up and running. Okay, second order homogeneous. We are going to look at, first of all, the homogeneous versions, all the different variances. So we are going to find our characteristic equations. So I'm actually going to do all of them at the same time. My characteristic equations are 4 lambda squared minus 7 lambda minus 2 equals 0. What we are looking for is, remember, what we are trying here, what we are trying is y is a e to the lambda x. That is essentially what we are trying here. Lambda squared minus 6 lambda plus 9 equals 0. Lambda squared minus 2 lambda plus 2 equals 0. So this one here, I'm fairly certain factorizes quite nicely. I'm going to go minus 2 plus 1. I think that's fine. So I get lambda is minus a quarter. Lambda is 2. Yep. So my two solutions here are y equals a e to the minus a quarter x plus b e to the 2x. Again, this is very much revision, not teaching you from scratch, but the idea is we are trying this every time. This one here, well, this is actually lambda minus 3 all squared. So what do we do if we have a repeat? We have the same root twice. So obviously one of the answers is, right, one of the answers is just going to be a e to the 3x. But this is a second order one. So to get that, we can have another e to the 3x, but actually how it turns out is we put a little x in front of it. And every time you have a repeat, you can just get another x in there. Now, what is the nicer way to do this is to factorize out the e to the 3x. So that is what we've got going on here. All right, so nice linear roots, perfect. Repeats, we're going to get x's popping their heads in. If it was repeated 3 times, which you're not going to have to do because that would be a third order, but you could just have x and x squared, not a problem. And this one here, that's lambda. Oh, look, this is very similar to something we did earlier. And if you know your stuff, and again, I'm not going to go into the full derivation of this. We get e to the 1x I possibly could have chosen them with slightly different numbers, but it's 1x each time because of that. So let's say we had got lambda is 2 plus or minus 3i, and by y I mean lambda. Just to make sure, we get y is e to the 2x times a cos 3x plus b sine 3x. All right. So again, apologies if you want the full derivation. That is not really the aim of today. Okay. So that is the actual answer to this one. This is just another example showing you where the real and imaginary parts go. Bah. Holy laggaroonie. Are we that laggy? Give me 1 second, boys and girls. Let's see if I can fix that. All right, Netflix has been turned off downstairs, so we'll see how that works. So these are the general solutions, all right, to these equations. You would need some boundary conditions, some initial conditions to find the A's and B's. We'll get onto that. But generally, these are the 3 cases for second order linear differential equations. So far, in this case, this is the general solution. How about if we have non-homogeneous? So now we have something on the right-hand side. Okay. So first of all, step 1, when we find the complementary solution, what we're actually solving is this. So I think what you're all basically asking about is the idea that our complementary solution, when we have a non-homogeneous, so non-homogeneous means there's something on the right-hand side. Okay. So the complementary solution is going to be the complementary function, if you prefer that. That will be the general solution of the homogeneous version. So it's the actual general solution of this one. Okay, so lambda squared minus 3 lambda plus 2. It could be complementary solution, complementary function, up to you really. What's that? Lambda minus 2, lambda minus 1. So I know that I can, let's see if I can get my x's and t's correct all the way through this. I guarantee I'm going to swap to y's and x's at least once. So I always start with the complementary first. Always start with that. Now, because this is linear, the idea is I can always add this complementary function on to any solution that satisfies that. Because basically, when I whack this in onto the left-hand side, it comes out as 0. So because it's linear, I can add that onto my other solutions and it won't affect the right-hand side. Glorious. Why is it important? Well, we're going to find our particular integral or our particular solution. You look at the right-hand side, it is linear. So we are going to guess linear. And yes, you heard that right. We are doing a guess. Other thing I tend to do, as you'll quickly see, is I will use capital letters for the complementary solution for those unknowns. And then I'll swap to lowercase for the particular integrals. It basically frees up a few letters for me. So dx dt is a, dx dt squared is 0. You've seen the dot notation, I hope. So let's plug that in. So I get 0 minus 3a plus 2 times at plus b is equal to 2t minus 3. Lambda, mu, and sigma, absolute maniac. And a bit like with complex numbers again, we are going to compare coefficients. So this tells me that 2a is equal to 2, which tells me that a has to be equal to 1. And if we compare the non-t bit, it tells me that minus 3a plus 2b a is 1, so I think b is 0. B is 0. So we know that x is equal to t is a solution. Now, I said I wasn't going to do too much teaching today and more like revision and trying to highlight a few ideas, but why do we want the complementary solution? Why do we want the complementary solution? Because I've already found a solution. Y equals t satisfies this equation. Well, the problem is, there it is. There it is. It was always going to happen, right? There it is. It was inevitable. Just be careful. The problem is this actual solution that will satisfy this differential equation will not satisfy my initial conditions. It will not satisfy my initial conditions, which is why the ability to whack on all of this gubbins, which still solves this, is still absolutely fine, enables me to make these works. So when t equals 0, x is 1. Cool. When t is 1, x is 2. And already this is, oh no. Unpleasant, but it's doable. What I'm going to do is I'm going to times this one by e. And subtract. Obviously. Unless I muck that one up. Ah. There we go. Is b 1 over e then? Or is it minus 1 over e? Minus 1 over e for b? Minus 1 over e? Yes. Yes. And you can plug all of that in to make something that looks vaguely not disgusting. Not sure where I've got space for it, if I'm honest with you. Okay. That is particularly horrible. You might need to differentiate it, right? You might need to differentiate it to get what you want out of there. But yeah, by and large, that's where we're at. Right, if you're given stuff in terms of dx dt, you might need to differentiate it, but all of that is fairly straightforward. Okay, let's see what we can do. SHM is just a particular form, right? SHM really is just a particular form of differential equations. That's all it is. And it's really when you end up with something like this, d2y dx squared plus omega squared y is 0. That is our basic form of simple harmonic motion. And the solution to that is a sine omega x plus b cos omega x. Okay, that is it. That is it. Now, there are some other things that are quite handy when you look at this. You could also, but this is more of a mechanicsy thing, you could call it a sine omega x minus theta. You could also do that if you really want to. But again, that's a bit more mechanicsy. All right. So all you really need to do is know this general form and start putting stuff in. So a particle is moving such that its acceleration is proportional. So we've got a particle moving this way, but its acceleration is towards the origin and is proportional to its displacement. All right. So that tells me that x double dot is minus kx. Yeah, x, y, y, x, x and t, you'll survive. Okay. Now we don't know what that is, but that's absolutely fine. I know that x is a sine omega t plus b cos omega t. And then we just need to plug stuff in. So x dot is a omega cos omega t minus b omega sine omega t. And then we can go t is 0. So when t is 0, x is 0 from this line here. And equation 2, x dot is 2. I mean, sure, right? It's minus. Now, why the omega squared, that's just to make sure that it's always pointing backwards. I just put k because it's proportional, but yeah, the fact that it's always acting backwards is why we square it, by and large. Okay? So our displacement will be 2 over omega sine omega t. What's omega? That depends. We don't know what the proportionality is in this case. Okay, we don't know what the constant of proportionality is. And that's completely logical because I've got 1, 2, 3 unknowns. I've only got 1, 2 bits of information. So there was always going to be something left hanging. But really, you need to, basically what I'm trying to say here is you want to be able to spot simple harmonic motion. This idea of x double dot is minus omega squared x, or y double dot is minus omega squared y, whatever it is. But so that way you can assume it. Am I assuming step 1? Because of what they've told me, this is basically what the question is telling me, right? The stuff in the purple boxes are equivalent, m's. From there to there, it's obvious. As in, the orange box tells me that. That is something that you can take for granted. You don't have to resolve it every single time. I mean, it's obvious to solve, right? It's just this case here with no real part. But apart from that, you're just solid. You can just do it. So there are lots of different things that can come up, right? What do I do once b is 0? I also plug t is 0 into x dot. There are lots of different ways that we can muck about, okay, to get velocity and acceleration. But by and large, SHM, all right, isn't too bad at all. Omega is just a constant. It's any constant you want here. You could put omega as anything, right? What do you do when function b is 0? Well, we find an expression for a and we plug it all in. Well, yeah, but this is like, yeah, Liam, but there's lots of different variants on these types of questions, right? When we get into closer to the exams and we're doing cram the night before, and we're doing the preparation sessions, and it's what we're going to be doing in the main course in 3 weeks' time, 2 weeks' time, not next week, not the week after, the week after. We're going to go be throwing exam questions. We'll be hitting a lot of these different cases. Okay, but really what it boils down to is this, right? Trying to remember which version of this is in mech, which one is in core pure, right? Should I work with x's with w's? I don't know. I'll work with the y's. If we write this in harmonic form, we'll get something like this, right? With an amplitude. But what you can realize here is you can then start doing like sine squared plus cos squared, things like that. Okay, but then you can start mucking about with it. But this is more on a question by question basis of how you want to do this, how you want to do that. Do I use the harmonic form? Because this is a slightly different A. Do I use this broken down version? That is very much on a question by question basis. The real thing for you is to be able to recognize when you have simple harmonic motion, really. Right. What time is it? 2 o'clock. I think we are going to leave damped oscillations for tomorrow. So our next free live stream is tomorrow at 10 o'clock. We will start off with damped oscillations. Hang on. Last thing for Sarah. If you rearrange this one here, you get A is 2 over omega. You got A is 2 over omega, B is 0. Plug them both into our expression for x. Right, tomorrow we will start off with damped oscillations at 10 a.m. We will go until 2, 2:30, 3 o'clock tomorrow. All right. We will finish what we need to finish. In the meantime, we've got more of this tomorrow, right? Another 4 hours. What you are missing if you aren't signed up either to our main course. So anyone main course students, I'm assuming Liam in the chat is just normal Liam that I know, and same as Cordelia. You have access to all of this anyway, so don't worry about it. But if you aren't already signed up to our full ERC course, beyond just the free stuff, like I've said before, you get all of the modules, S1, D1, FP1, M1, all the 1 modules. There's only so much time in the week, with past papers for all of them, fully worked solutions, recorded sessions all the way through, and all your workbooks. How much does that cost? All right, so these are all the different, here we go. So one subject is £49, but it does get significantly cheaper if you're doing multiple subjects with us. So if you are also looking at doing the maths already, it's a lot cheaper. If you're doing maths and physics at this point, it's a lot cheaper. It comes in at £33 per subject. All right. For another 8 hours plus of revision, solutions, fully worked things for every single paper, me working through it for you. So that's all available for you. Kian, the main course is not where I would not suggest signing up for the main course, because basically what we're doing in the main course is for the next 2 weeks, I'm finishing off D1. Then I have got 1 week that you would miss out on doing a bit of core pure revision. But after that, we are into the exam masterclass, which you can sign up to. I will be putting information and slides for that up. I can put some up tomorrow if you are interested, so you can go have a look at it. The exam masterclass will be a pre-revision session, so it's always 2 sessions for each thing. So for core pure, we will have a bumper 4-hour, let's do a little bit of pre-work 2 weeks before your exam, the actual papers are. We'll go through some highlights, what to look out for, how to prep your revision, and basically the same sort of vibe as today, but with very much specific exam questions in mind. So a bit less general as today and tomorrow. And then the night, so we'll do that for every module. We'll do 1 for the core pure, 1 for mech, 1 for stats, 2 to 3 weeks before the actual paper. And then you get the cram session, which is off the top of my head 4 hours the night before the actual paper is. So if you've got the paper on the Thursday, Wednesday evening, 5 hours, we'll just be going through exam questions, bosh. You can ask your questions a little bit more Q&A focused, where we really drill into how to get the marks and things like that, as well as a spec breakdown for each of the modules with links to actual past papers, as in if you want to practice this topic, go check out Edexcel 2024 question 3, whichever it is, and links to video solutions of me working through similar types of questions on which are currently available on TikTok and YouTube, so to help guide you through there. So the crams are part of the masterclass. Yes, the masterclass is 2 parts really. Well, 3. You get the 2-week, 3-week before pre-session. You get our revision guide workbook, which has spec breakdowns, links to papers, formulas, things like that. And then you get the night before cram. So that is all part of the exam masterclass. I'll put a bit more information for you for that one up tomorrow. So there we go. Do I do further pure one? Yes, I will be doing further pure one on Saturday. I'm doing FP1 for the Easter revision, and then there will be an exam masterclass. I'm doing all of the modules for the exam masterclass. Brilliant. So those of you, I'll see you tomorrow, hopefully 10 till 2 for more fun maths. Hopefully you'll keep me on the straight and narrow tomorrow as well. You've been absolutely wonderful today, everyone. You've been really helpful both to each other and to me. 4 hours is a long time to keep going. But keep talking. My throat is going to go. But brilliant. I will see you then. No, so the prices up on the slide at the moment are for the rest of the Easter revision course, for the modules, basically. So the modules plus, the other thing, it's not just the modules, it's also full access to the streams from today and tomorrow up until the exams. These will be online for another couple of hours this afternoon until this evening, and then they will not be publicly available for free. All right. They will be available via the MyEdSpace platform in the part 2 of the ERC. Brilliant. Hopefully this was good revision. I'm going to go enjoy Octonauts, probably something like that. It'll be lovely. Matthew, you are most welcome. You've all been amazing. Very productive, all of you. So hopefully that all works out for you. I've really enjoyed it. I love doing a bit of maths. It's really chill. We'll do some more tomorrow. It's a bright sunny day. Go outside, get some fresh air. I don't know, do something fun, do something silly. Ade, I will be able to give you, I don't know the pricing for the master classes off the top of my head. I will put similar information into our slides tomorrow. So just remind me tomorrow and I will be able to bring that up. Okay. Time for the out of context videos. No, CubeCore. Got to wait until we've done tomorrow. There will be even more absolute rubbish coming out of my mouth tomorrow. Right. On that note, boys and girls, see you tomorrow for, do not let me forget, damped oscillations.